slides, so you didn't really miss much. I had a funny feeling because the software usually puts this green bar around. Okay. And I think the problem is when I go into PowerPoint mode, I can't see. Let me try to move this thing up here. Okay, let me just make sure everything else is cool. Can anyone see them? Okay, yeah, so I only made it in a couple slides. I'll just back up here and show you guys real quick. I'm glad I stopped there. Okay, close that out. Down to there. Okay, this was the intro slide. And this is the Advanced Spark TensorFlow meetup. So if you're looking for old resources, I mean, they're not too old. I pretty much do a meetup or two every month in some city somewhere, and all the materials flow back here. Introductions. And so, yeah, you guys hopefully have some working knowledge of TensorFlow, but it's not required. And I was basically talking through all that, and this is the current slide. Okay, someone's raising their hand. Let's see. And, let me find the chats. Okay, I think I'm going to have to move ahead here. Someone's raising their hand. Yeah, Matthew, do you want to either send me a note directly or the attendees? Are you okay? I'm going to lower the hands here, but shoot me an email. Okay, everything's good. So I just lower the hands. Let's go back. Okay, I'm going to start this up again. So 50% of the content will be about training time optimization. So this is things we can do to converge faster, to speed up training, to do training in parallel, to do things like hyperparameter, like tuning and grid search. And these are a lot of the features that the Google Cloud ML offers. So of course we're tracking right alongside that. I mean, these are the same issues I saw when I was with Databricks, same issues I saw when I was with Netflix. People, it's oftentimes more important to get through a training run quickly, even if it's not at full precision, for example. And we'll talk about some of the half precision stuff here. But what you want to do essentially is, have multiple hyperparameters. So, and like neural nets, the obvious one is the learning rate. If you can run two experiments at the same time, one at 0.025 and one at 0.05, if you can run both of those in parallel, and because there's a lot of this sort of black magic, right, where you don't exactly know which parameters will work, and sometimes some just don't work at all. And so you want to know this quickly. So typically what you're doing is either training on a smaller set of data, or you're training on the same set of data, but at different precision, just to get through it faster, and at like lower precision to get through it faster. So also there's this new feature by TensorFlow. It's called XLA, the Accelerated Linear Algebra feature. And this thing specifically, it's very similar to Spark and Spark's Project Tungsten, if you remember this. Where in Spark you kind of build up your graph of operations that include maps and filters and joins and sorts and things that you would think of in big data processing, right, and sort of ETL pipelines. And the Spark guys realized that if you can combine things, so you write your logical plan, which would be in code or even in SQL, because Spark supports SQL. That logical plan can be analyzed and can be sort of rearranged in a smarter way. So no matter how you actually build up your graph, if you do a join before you do the filter, right, that's obviously not optimal. What you'd want to do is filter out things before. So Spark is intelligent enough to actually rearrange. So that's some of the Catalyst Optimizer is the name of it, query optimization. But there's a low-level optimization that's also being done outside of just the normal query optimizations, where maps and filters can actually physically be combined into one physical, right, like Java method. So Spark is all Java Scala based. And if you could literally look at the logical plan and see that it's doing a filter right after a map, Spark now, as of Spark 2.0, can actually break or can fuse together those two into one physical Java source file, and then on the fly dynamically compile it with this project called Project Janino, Janino, which is an open source project that Spark kind of picked up and made popular, and all of a sudden now Janino has this really fancy website and everything. It was kind of a dormant project for a couple of years, but it works really well within IDEs, and it'll actually compile it within the IDE, and then you can debug and step into it and set breakpoints and all that stuff, whereas some of the other options like Scala, like what's it called, quasi-quotes and things like that at the time anyway, didn't work very well within these IDEs. With the XLA, this is doing something similar. This is during training time, right? During processing time, when it's churning through this data that's coming in that we're trying to train on and learn from. TensorFlow can actually recognize common operations that are being done together and can fuse them together. So we'll talk about that pretty heavily, but that's kind of the general concept. Anytime you hear XLA, if you're familiar with Spark, just kind of swap in Project Tungsten, and you should be in good shape there. So the second half, and this is different than a lot of the workshops that you'll see and see online and be a part of, is deployments and the inference. So this is the prediction side, fancy way of saying, right, like prediction is, right, the inference. So this is after the model has been trained. And now what can we do with the graph? So yeah, I'll show an example later where we're going to use simple models, which is that very last bullet point. And I do that on purpose. I don't want to get bogged down with convolutions and sort of, complex, right, like the recurrent neural nets and things, because that's not the point of this course. There's so much material out there that right, like covers that stuff. This is, right, like once the model's been built, right, like I'm going to show you guys how like crazy big that graph becomes, right, because of a lot of things injected during training time, like dropout, like batch normalization, right? These are all nodes within the final like TensorFlow graph. And I've got a tool that actually renders it right inside of a Jupyter notebook. I highly recommend that you snag that code and use it in your own stuff. It's very helpful. We'll talk about some ways to trim down that graph, because we know that we're going to be serving this graph, right? If you're going to continue training, if you're just stopping training because you're waiting for more data, you don't want to do these like sort of inference optimizations. Like this is only for when you are ready to actually deploy. The goal is to get that model down as small as possible. If you can even like reduce the precision, maybe get it down. So I was talking about half precision before for floating point. Full precision is 32, half precision is 16. If you can get it down to half precision, that's going to greatly reduce the size of the model and also improve some of the like performance when you're actually doing the prediction, when you're doing the forward propagation, right? So training is forward propagation. You compare it to the answer key or the label of the trained data that you're passing in. Then you back propagate the specific errors and use partial derivatives to assign and make changes to weights that were more influential in the error of the forward propagation, right? So that's the whole concept here with these neural networks. So So yeah, with these inference optimizations, what you're trying to do is make the physical model smaller, and the goal here is to put it onto a device, not your phone. Phones are huge in terms of like memory. But we're talking sensors, we're talking cameras, we're talking really really small devices. So trying to get models down into the the 100, 500. Maybe 1 meg, right? Yeah, so 100K, 500K. That's what we're going for here. So we'll show some examples there and physically do these things on our simple model and make some huge changes. I think that the simple model, when it comes out of training, is about, when I remember, I think it's 20K. Which is small, but it's this very simple model. And by running 1 or 2 of these post-training optimizations, that quickly goes down to, I think, like 100 bytes or 140 bytes. So, kind of gives you sort of a relative scale of what these tools are capable of doing. Okay, and why is there this heavy focus on the inference side of things? For my personal experience and sort of interests, I have a lot of Netflix experience and like distributed systems and microservices and high scale and monitoring these services and keeping sites up, right? So not in the DevOps sort of way, but in what can a developer do or in this case a data scientist do to keep these models up, right? What kind of tooling can we give them to make the models smaller, to like make the models faster, and hiding a lot of this complexity, which is the exact thing PipelineAI is doing, which is why I love doing these workshops, because it's like it's kind of taking our most current research, that's being pushed into the open source project and being pushed into our project, and it's like directly explaining it like to you guys at a lower level than you would normally get. Yeah, also too, sort of if you think of Big O, the number of people that are affected or that are using the training aspects of these pipelines, I guess you would say, right? These like AI pipelines. For training, this is the number of data scientists, right? It's the number of your researchers. And if there's, small companies have a handful. I think, was it Facebook is famous for having 60, this company Stitch Fix that I work with a lot, they're, I think the number of researchers there is actually quite high. I think they're even close to 100 or maybe 80 for being such a small company, but they do quite a bit of machine learning and some pretty exciting stuff. So I've got a couple of friends over there, a couple former Netflixers that are running the team over there and that kind of thing. So Big O on the inference side. So this is every prediction. So this is like n times the number of users of an app, because it's not, each user, as they're sort of navigating the app, the website or running searches, and they're going to run, n number of searches each session. And so if you're Netflix and you have 110 or 120 million users, and every page that they click is being personalized or trying to be optimized for your experience to get you to click and to watch movies or to buy an Amazon product. This is huge. And I sort of highlight here batch and real time. With training, a lot of shops I work with, when I talk about sort of latencies and the SLAs with training, and people are typically like, well, if it breaks, I'll just come in the morning and then restart it. These are typically customers that they still haven't fully bought in to like machine learning, right? Like maybe this is powering one part of their app. If it's not there, if it's not totally personalized, it's not that big of a deal. Places like Netflix, places like Quora, places right, like Amazon, right? These bigger guys, this is their business. Their business is machine learning, and if and they treat their batch jobs as though, you know, they are real-time jobs, right? If these things are down, they get alerted. You know, it's not good enough to have recommendations for your users from 1 week ago because there's some kink in your training pipeline. So starting to see some of, you know, training actually becoming more real-time. Still, you know, there's a couple customers that we work with, particularly in Europe, that are heavily experimenting with online training. If you're familiar with scikit-learn, you're familiar with partial fit. On some of these linear models, right, like linear regression, logistic regression, you can actually train in what's called partial fit mode, which means you're sort of never really done training the model. You are always considering the data that you're passing in to be partial data, and it's just going to train in sort of like a mini batch, I guess you would call it. If you just keep passing in data, it's just going to partial fit, partial fit, partial fit. Kind of have to be careful there because depending on, you know, the randomization aspects of this data that's being partially fit, this model could start to learn wildly different, you know, weights and findings depending on these batches coming in. So kind of have to be careful. Typically, people put these behind Kafka streams, and there's enough randomization there. In most cases, you know, if there's some big events, like for example Netflix, if there was and if the what was the one? I think when the Super Bowl ended, for example, you know, suddenly there or it was no, it was I believe it was the Oscars. When like the Oscars would end, all of a sudden we got a huge influx for like requests for the same 10 movies, right? The top, you know, 10 movies that won the Oscars, or the top 5 that were nominated for Best Picture, something like that. So yeah, so things like that you have to kind of be careful of when you're doing real-time training. But at this moment in time, I think more of the challenges are around the real-time serving, because that's the part that's actually affecting the user experience. And if something's going wrong there, what you want to get to is a state where if this real-time service goes down, if this REST API goes down that's serving up your TensorFlow models, you want to have fallbacks in place and circuit breakers and things like that. These are like architectural patterns. I have demos of these later on that will show. These are really very, very heavily influenced by Netflix. They have this library called Hystrix that makes these fallbacks a first-class citizen. We're moving right now actually to a state where with PipelineAI, you physically cannot deploy your model unless you have explicitly defined some fallback. And this is kind of a pain for some people, and then the first time that you see it in action, you're like, thank God I you know, put that fallback in place, right? So we have things like Chaos Monkey and Latency Monkey and things like that once they do deploy their service, we point these tools straight at production. We, you know, drop their services. We introduce, you know, 5-second latencies to make sure that the people calling in have timeouts, and you know, so really putting a lot of Netflix sort of high availability techniques into our services, and not just putting them behind a Flask app and, you know, like forgetting about it. And then the other aspect too is just having insight into these predictions and into these model servers. So all of our models that get deployed into Pipeline, and yeah, this is all open source stuff that I'm talking about right now, have dashboards. We're using Prometheus, Grafana, and we track how long did it take to convert the JSON into NumPy, how long did it take to actually run the prediction, and then how long did it take to convert the prediction back to JSON to send the response back. So that's sort of the web REST sort of API transport. We also have similar things for Kafka, right? Where we, how long did it take to convert the Avro into whatever model you're needing? You know, if it's a scikit model, maybe pandas, maybe NumPy, if it's TensorFlow, you know, yeah, how long did it take to get it into a physical tensor that can then be used by TensorFlow and then go in the other way as well. For the Kafka case, we actually run the predictions using Kafka streams and then put the prediction on another topic that then gets absorbed by the application teams. So right, like again, we're using simple models. The goal here is to highlight some of these techniques that you're not going to get elsewhere. For the most part, this is not intro material. There's a couple slides where I am going to level set and talk about some of the key terms and terms specifically that are used inside of TensorFlow, that if you were reading a research paper and then you have the TensorFlow version of the code, there's going to be quite a heavy mismatch in terms, and I just want to bridge that mismatch. So there's going to be the code, there's going to be the TensorFlow documentation, and then there's going to be the research papers, and just kind of give you guys the similar terms and things like that. Okay, so all this is open source. I think I just took a snapshot last night, 1,700 stars, pretty excited about that. The VCs love this kind of shit. The map on the right, there's some site you can go to that'll actually generate this. It'll slurp in your contributors and forkers and people who starred, and it'll actually show on the map kind of the hotspots. So obviously San Francisco is a hotspot, a lot in Europe, a lot kind of throughout the Midwest there too, the US, a bunch in Australia. You can't see it here. It looks like I kind of blocked it out, but I've got a little blip down in Brazil too. So yeah, I'm excited. I think I'm going to head out there pretty soon here and say hi to that right, like local community in Rio and Sao Paulo, things like that. Okay, so everything that we're using today, the Docker images, the code, the slides, the notebooks, everything is within this within this GitHub repo. There's instructions inside of that repo on how to get this full environment, including the GPU instances and how to set up CUDA and how to basically get all of this running, okay? So after today, yes, you guys can go and actually set it up yourselves. For the hands-on exercises, it's going to be Jupyter notebooks. There's some things that we have to do within command line, which I know kind of bothers some of the data scientists. They don't want to run, shell scripts and things like that. Just either close your eyes, take a break, or follow along, or or just jump in and do them. Some of these exercises are actually a good portion are based on the experimental features. These are features that currently within TensorFlow are the experimental features. They will, in the next 2 to 3 releases, they'll be turned on by default. And some of that is the XLA stuff where I was talking about the operator fusing and Spark Project Tungsten. Spark did the same thing. They turned these things on in the experimental mode and let people play with it to get feedback and see how people were using it. And then they turned it on by default. So we'll talk about a lot of this, but just please, bear with me. There's going to be errors. We will all get through them. If there's a huge blocker, I've got you all set up where every instance is connected to GitHub, and I can make a change and push it out, and you guys can all slurp it in. That's a little tip there for anyone who's thinking about doing something like this, training at scale kind of thing. It's a very powerful concept. All right, this is what we're going to learn. We're going to inspect and debug models, talk about training and predicting best practices with TensorFlow. We're going to do a little bit of distributed training. We're going to use queues and to actually saturate our GPUs and our CPUs during training. This is hugely important to try to get through your training quicker so that you can figure out what you messed up in terms of hyperparameters, or possibly might have to change the actual architecture, right? Like the actual network architecture, because this itself is a hyperparameter, right? Like which nodes talk to which nodes. So it's not always learning rate and some of the simple things that you would tweak. It could be the actual connections. let's see, we have a couple workbooks on the XOA stuff, so we'll show kind of before and after and some of the benefits there. And then these last four bullet points are actually after, so you see the word inference in there. This is after the model has been trained. Now we're ready to push these into production. And what do we have to do to squeak out the best performance possible, right? So there's this AOT compiler, which is, that's ahead of time compiler. That's different than just in time, right? So with an AOT, and yes, AOT is also built on XOA. So with the AOT, we're actually going to take a look at our final model, our final graph, and have TensorFlow run through it as though it was doing the forward prop, and literally pull in only what's needed from the TensorFlow runtime. So it's, just going to pull in the matrix multiply. It's just going to pull in, right, like the bare minimum that's needed to get you from when you pass in the input to, which is going to come off of a JSON request, right, like a REST request, to the output. And so I'll talk, and it's literally going to just pull in what it needs from TensorFlow and from the actual operating system, right? So the kernel methods needed from Linux, and it's going to bundle that all up as a C library, including an object file and a header file that you can actually embed into your small device or your phone or even like a desktop app. But this is where you see models go from what would normally be about 80, 90 meg at runtime, because the TensorFlow runtime itself, if it's running fully, right, like it would be within TensorFlow serving, for example, is about 80, 90. Oh, so the actual runtime is about 40, 50 meg. And then if the model itself, because it hasn't been optimized, is 30 meg. So now you have 80 meg. I've seen models with this AOT go down to 600K. Okay, and that's including all of the runtime binaries, not just the model itself. So these are the kind of tips and tricks that I'm trying to surface, and these are things that are going in, or that are in PipelineAI. When you upload your newly trained model, it's going to do a lot of this stuff for you, so that you, as the data scientist, or as just the Jupyter Notebook user that just wants to deal in Python, you upload the model. We then do make these changes and then spit you back, so not just the optimized model, but actual different forms of the optimized model. And so we say what we did, right? We stripped out these nodes here. We did weight quantization here. We dropped the precision on this third version, and we did the AOT on the fourth version. And you can then deploy all four of those. You can load test them. You can have a big dashboard. You can even compare them to a version that your scikit-learn Python guy built, or someone who's using PMML. So yeah, we support all these things. If someone wrote it in R, you can actually deploy all 6 or 7 or 8 of these different versions out into PipelineAI, and then have a dashboard that'll, and you can load test it and then see how it's doing. And then the other thing with Pipeline 2 is that you can actually put these out into canary mode, into your live data, your live cluster, and you can have 2 different types of canaries. There's a shadow canary. So shadow canary is just getting some of the data, like maybe 10% of the data is being fed to the shadow canary, and it's just going to score it. It's going to log the inputs, it's going to score it, and then log the outputs. And then there's a separate dashboard that's going to show you the actual predictive performance of all 8 of those models. And you can then see and make sure maybe the PMML model is scoring wildly out of tolerance, right? So you would ditch that one, or maybe go, or say the PMML one was faster on the runtime. Maybe the Java JVM JIT compiler was able to get huge performance gains, but the predictive performance is crappy. So you can then decide. So this is the kind of insight that we're trying to give straight to the data scientist, right? And not have to go through ops and an ML engineer and yeah, that kind of stuff. So okay, and then the last three are TensorFlow serving and some of the optimizations there. If you're not familiar with TensorFlow serving, I would recommend at least trying it out. There's a lot of people that are just putting TensorFlow code behind a Flask app and not using TensorFlow serving. They're just putting Python code right behind and building up the graph and creating a session. Just so you know, when the second that you create, if you call TensorFlow's new session, that actually incurs a 200 millisecond latency. And so I was working with the OpenAI guys recently on how to get that number down. So there's techniques when you're actually using it that way. If you're not using TensorFlow serving, the OpenAI guys had an issue with some of their recurrent neural nets and some of their reinforcement learning algorithms that TensorFlow serving wasn't performing very well. And they ended up just putting it behind like a Flask app kind of thing, and they noticed that a lot of time is being spent in just creating the session and calling session.run. So yeah, so I spoke to one of my Google Brain buddies who explained how to actually get in there. And if you want to know about that stuff, let me know. It's kind of out of scope for here, but yeah, I can definitely share you guys some of those techniques. And I think some of it's actually out on Stack Overflow and stuff like that as well. But just be aware of that TensorFlow serving, it's definitely worth a try. There's a lot of support going into it. There's a lot of knobs you can turn. We'll turn some of those later. Some of the request batching you can turn on, and different strategies for supporting multiple models at the same time, multiple versions, A/B testing, things like that. There's quite because this is exactly what's powering the Google ML engine, right? So Google's been kind enough to give us a whole ton of the new features that show up in Google ML engine end up flowing through TensorFlow serving open source, which is really nice. When I first started Pipeline, I was actually starting to build a lot of this stuff on top of TensorFlow serving. My thinking was Google would never release their A/B testing framework or their multi-arm bandit testing framework, and they would just keep it as simple and dumb as possible. And then Google Cloud ML would actually have all these cool features. And then one day there was like a 1,000-line commit by Google saying, oh, by the way, here's our experimentation framework. Boom. So, and I finally see the value in that. They have to release the APIs so that we, the model creators and model developers and data scientists, we can code to those APIs, the experimentation API, and which then the Google ML engine can now interpret, and it's a first-class citizen basically. So by giving us the first-class primitives, their engine can then serve them up. So kind of makes sense. Yeah, we'll actually deploy a model, and we will tune the runtime and turn on request batching, things like that. Okay, so let's get at it here. GPUs and TensorFlow to start off. Everyone's getting a GPU. We got Oprah there doing her little Christmas special. So one thing here, let me see. Okay, so go to this URL. Please just go to it once. Please, please, please. I've spun up just enough for all of us. I did about a 10% extra, but I want you guys just hit it once. If you're all hitting it at the same time, it might actually, it's just a crappy Python app behind the scenes. And this should serve you up a IP address. And all you got to do is put that IP address directly in your browser. Yeah, hang on here. Made that smaller. Pipeline.io. And I'm going to keep an eye on the chat here. Let me know if you see anything wrong. I'll actually put this in the chat as well, so we can come back to it. It's HTTP. And let me look and make sure the app is running properly. Okay. Yeah, it looks like people are being allocated. Okay. So pop that IP directly in. And I'm going to actually sample one of these and just make sure that your guys started up okay. Mine started up good. Yep. Okay. So success in this case would be get to a page that looks like, let me get to the screen share. Get to a page that looks like this. Okay. Oh, it looks like a couple people started the repo. Yes, please start it. That would be wonderful. I'm going to give this a minute. If there's anyone having problems, pipe in on the chat. For those of you that are exploratory, you can kind of click around. I'll give you guys the password and stuff here in a sec. I want to make sure everyone's synced up. There's a natural barrier here. Make sure TensorBoard is working. Okay, board looks good. Anytime you get lost, just copy and paste and put the IP address in your browser. There's an Nginx or an Apache server. Oh, you know what? I did put the URL in here. I didn't do all attendees. Sorry about that. We have Spark. I don't think we're going to do too much Spark today, but it's kind of fun if you want to. Both I've got HDFS set up here as well. Both TensorFlow. So TensorFlow now supports HDFS, which is really important, especially for the distributed case. And one of the funny things about dealing with Google in such a popular open source project is that they've never really been open source, right? They created a lot of the papers that led to all of these open source projects, but like initially when TensorFlow first came out, there was no HDFS support and there was no Spark support or anything like that. Hadoop support. You talk to them about Zookeeper, they know of it, but they talk about Chubby, which is the paper that led to Zookeeper. So when we get to the distributed section, we're going to talk, any distributed system, Cassandra, right, like Redis, right, like things like that. There's so many, Spark, there's so many failure cases that you really have to be pessimistic when you go in and think of all the failure scenarios. So right now, distributed TensorFlow is not very easy. They claim it's getting better, and they claim if you use Google Cloud ML that it's a lot better because you don't have to think about it. But they're essentially using Chubby, or in our world, the open source world, it would be Zookeeper. And anytime the leader goes down, a new master is like elected, and things like that. So we'll talk about all that stuff. Distributed training. That API is changing quite a bit and is evolving swiftly with Keras. So Keras, earlier this year, February, I believe, was the TensorFlow Dev Summit, the first one. Google hired the developer from Keras project and is now tasked with building native bindings for Keras. So Keras is a high-level API that was meant to abstract you from knowing if you're using Theano or Caffe, or right, like letting you run the same code and plugging in a different backend. And so, Keras had existed before TensorFlow. When TensorFlow came out, they decided to build the adapters for TensorFlow, and in doing that, Google realized the value of this project and also wanted to have not sort of lowest common denominator across all the different frameworks, but wanted TensorFlow to really, or for like Keras to really take advantage of TensorFlow distributed and some of the lower level constructs that are in TensorFlow, just to get the performance where they would like it to be, and the ease of use as well too. So one thing we spend a lot of time on at Pipeline is making distributed training with both Spark and TensorFlow much easier. So if you use Databricks, things like that, you'll see some of that stuff starting to creep through. We're laser focused on deployments, but we realize that when people go to deploy, that they need to actually train a model as well. So and with Kubernetes and Jupyter Hub and things like that, things become a lot easier. Whereas they were kind of a pain a couple of years ago. Okay, so I think if everything's going, you guys are probably at this screen here and wanting to get in. Let me close that. This is my session from earlier. Actually, which one's mine? That's fine. That's the other guys. Okay, so we all should have a unique IP. Go back to the slides. Share this. Boom. Okay, so we got thumbs up. Everyone's cool. Good to hear. Okay, if you need help, please use the chat. Make sure you include, looks like Rahul is just emailing panelists. Yeah, so Rahul, if you can change yours to be all panelists and the attendees, that would be awesome. Okay, so just verify the setup. This is what I was saying before. If you guys want to get in there, go in as root. So again, there's you each have your own GPU instance. Physically have one GPU that is isolated from, and it's attached to a Google Cloud instance that has 4 CPUs and I believe 30 gig. It's plenty to do the stuff that like we're doing today, which is just simple models. But these are all the tools installed. Spark's in the upper right there. If you want to try at one of the breaks, you can actually use this library I'm going to show here in a bit, where you can write from Spark. You can import a package. Maven coordinates are going to be provided here in a sec. And you can, at the end of your training, or at the end of your ETL within Spark, which is what Spark's good at, and you can then write out the data. If you take in a CSV, munge it, do a little feature engineering, and then write it out using a TensorFlow library for Java, you can write out in TF record format, which if you're familiar with like sequence files, back in the Hadoop days, and it's a first class, it's basically highly performant record format meant for sort of neural network type training, right? So it'll take your images and it can convert them into TF record, and then you would start up TensorFlow job, which would then read the TF record from HDFS that was put in there from Spark. And so like they can all talk to HDFS. Excuse me. I was trying to mute fast enough. I couldn't mute before my sneeze. Okay. So get on in there as root. And let's take a look at the first explore. There's actually going to be, so there's the explore environment. So let me, oops. Yeah. Go back to here. Where did my browser go? I'm just going to do my whole desktop here. All right, so killing that. Back to here. My IP. Oops. One sec here. Just want to make sure I'm on the right instance. Yeah, 254. Okay. Okay. So I'm going to click on Jupyter. As a special treat for you guys, I just got back from PyData in Seattle yesterday, and I saw the latest Jupyter lab. Actually, I think this is one version behind the absolute latest. I was having an issue with the absolute latest. So this is Jupyter lab. Someone's chatting me up here. Too long. Okay, Darius is I'm unable to access Jupyter on my instance. Okay, Darius, can you hit that URL up there one more time, the allocate URL, and get yourself a new IP? If you're having problems, occasionally, yes, every now and then an instance gets jacked up. I don't see it too much anymore. When I first started using Google a couple of years ago, I would see this from time to time, but line to respond. Yeah, so give that a whirl. Okay. And if you want the other like attendees to see what you're saying, just make sure you do the drop down to speak to all panelists and the attendees as well. That way my friends can help out. Okay. Yeah, someone asked, are all these features available in the community version? Yes. So yes, this is essentially like a snapshot of Community Edition meant to run on a single node. So yeah, I mean, everything here is open source. So there is, I'm using the exact same Docker image that I just built it right before, about 7:30 Pacific time here. So right before the start of the workshop. It's the exact same thing that some of the, slick UI and slick tooling and stuff like that is going to be held out. Some of the experimentation comparisons and some of the automated canary comparisons, if you push out multiple models, it'll run, like a bunch of like metrics and analytics and that kind of stuff is what will go into the advanced edition is what we're calling it. Just because I can't stand the standard word enterprise, so I'm trying to use something else. Okay, so let me close out this again. It's a little bit distracting there. Okay. Okay, so so this is Jupyter Lab. Jupyter Lab is kind of the next generation Jupyter. It's pretty much, so I believe once you're actually in the notebook, well, no, yeah. So actually they have these sort of nice constructs on top of the notebook, these, sort of outlines, and you can expand and like collapse the output and all kinds of cool stuff. So here we're using Python 3. I believe I have R in here as well too. If you want to play with R later, but yeah, for right now, we're going to stick with Python. So let's just make sure we get the latest code. Okay, we're already up to date. I know this for a fact because I just built this image. One thing, during this workshop, you're going to experience or see a few kind of magical scripts. And, I do lots of training myself where I get trained, and one of my pet peeves is magic scripts, because to me, that's the stuff I want to see. So I'm going to show you guys right up front. There's this, so within a notebook, by the way, you could do % bash, and then everything inside of here will run as though it's a bash command, which like it is. The other way to do it is if you just put bang, and then you can do it this way. So I'm using this command which some people may or may not know about, but if you do which, it'll it'll scan the path and tell you what file this is specifically. Okay, so I see that that's the file. I want to actually, now I'm kind of curious. I see that file. Show me. So do an ls-l. Show me what else is in there. Yeah. So these are the 7 magic scripts that we'll be running, and I'll explain them here. But and then if you're really curious, you want to see what's inside, you could just do a cat, and all it's doing is hiding. You know, if it's just basically forcing the poll to like overwrite anything locally. So I wouldn't use this too much. You shouldn't have to, not unless I have to push out a change. I was making changes right up to the start of the class here. So okay, and then here's just a quick way. You know, I like this because there's a lot of people that don't know you can actually embed iframes. So here's PipelineAI. You can actually you know, kind of tool around there. Actually, since we're talking about it, the very bottom here, it's covered up by the help thing here, but these are all, this is the meetup link, that's the YouTube, that's SlideShare, there's GitHub, that's my LinkedIn. I think it's my LinkedIn, or maybe it's the company's LinkedIn. And then, yeah, all code is in the repo. Here's the meetup. One thing, just for sanity check, make sure this runs and gives you the same IP address that you have up here. And also, this should also do something. So mine is 0. We may or may not use this later. This would be used in the distributed cluster. We usually don't have time for it, and it requires a lot of setup. And from what I've heard, it's more sort of engineering and less about the focus of this workshop. But kind of, oh, and so just so that you know, this isn't like this is an internal. So Google gives you the ability to inspect the instance that you're on. And this is kind of a special IP that's kind of like a local host thing. There's this daemon running out there that, you know, can give you metadata about your instance. Yes, Amazon has the exact same thing. I can't remember if it's the same like IP address or not, but like essentially tell me which region am I, what, you know, which zone did I get placed in, things like that. So this is pretty useful if you're doing things like building a discovery service and you want to make sure you have, like verify that you have instances running in different zones. So, you know, for the high availability situation, for the fault tolerant situation, that kind of thing. So, yeah, kind of wanted to point that out. Yeah, and then just real quick too on, okay, so I'm on files here, right? This files tab. Some of you might be trying to make this smaller, which is really annoying. I actually almost stopped using JupyterLab because I couldn't figure out how to make this sidebar smaller. What you do is just click on files up there. It's kind of like the accordion control. It's not obvious at all. But if we click run, this is going to come in handy later because we're actually, the GPU will get wedged. It's going to end up getting out of memory. TensorFlow, this is why I have you all on your own separate GPUs and we're all not trying to share a GPU. TensorFlow is very greedy. It's very selfish about its use of the GPU. It expects all of it. There's ways within TensorFlow that you can kind of tweak it and say, you know, only allocate up to, you know, 40% of the GPU, or, but I haven't had very much luck with it. So GPUs for big data and for TensorFlow are still in kind of a wonky state. This is a lot of what Pipeline's trying to do to, you know, try to hide you from that pain and just let you, you know, compare models and treat the fact that it's a CPU or a GPU as just like another hyperparameter, basically, right? Just another attribute that you have control over, but you don't have to deal with the OPSI side of things. This is a little bit different too here with, there's these commands, some cell tools. I don't really spend too much time there. And then this is your open tab. So you can click on tabs no matter how many you have going across here. You can click on this and go right to the one that you want to go to. So that's kind of cool. JupyterLab will be coming out in beta, which actually for us users is the full release. It's a GA release for developers. Some of the APIs might still be changing up until, I believe it'll be the end of the year before JupyterLab is actually API frozen. But it's kind of a nice little tool on top. Okay, so we got through this first one, was pretty easy. Let me jump back real quick to the PowerPoint. Okay, just a real quick, I like this little feature of Zoom where I could do a poll. So I'm gonna ask, pulse check, how are you doing? And the answers will be good, not good. Okay, if you guys want to tell me, and good meaning you are set up okay. We're about to kick into gear the pace of this, and it's going to get pretty technical pretty quickly here. So, okay, we have one person saying they're not good. Clicking run, but nothing happens. Notebook code not executing. User is root, correct, no password. Clicking run, nothing happens. If you get, okay, so Bernie's having an issue, it looks like, where he's clicking run. Bernie, and for all the others, if you do get into some weird state, can you click on this little swirl thing here? It's kind of a restart kernel. Do you wish, oh yeah, so it's going to be the swirl inside of the actual notebook, at the top of the notebook. All variables, and then you should be able to run it again. And run, oh, if you do Shift Enter, right? You can also, I believe, hit this plus thing. I don't usually use the plus. There is a way to run all cells. It's not as intuitive as it was in the old Jupyter, just straight up Jupyter. You do run all cells like that. That's notebook, run all cells. Okay. Okay, so yeah, Bernie, I'm going to keep going. We're going to take a break here in a bit. Okay, someone's raising their hands. Yeah, Al, do you want to chime in here? Tell me what's going on. Yeah, Bernie and Al, can you guys post to the whole group, all panelists and the attendees? But I think I'm going to keep moving ahead here, and at the next break, which is just in a couple seconds. Oh, the login code. Okay, it is username is root. Send this to everyone. Password. There is no password. Password is nothing. It's blank. So root and just nothing for the password. That should get you there. Okay, so let's keep going. I'm going to end this poll, and might do one or two of those later throughout the class to make sure everyone's. Okay, so as I mentioned before, TensorFlow and essentially any GPU setup installation for your sort of training jobs and things like that is very, very difficult. Fortunately, I've built all of these Docker images, so you can go, if you go to pipeline.io, there's a section on GPUs plus performance. If you click on that, it'll guide you to the Docker images. It's not just the Docker images, and I'm very proud of this. It's also the installation instructions. So it takes you from provisioning a cloud instance, so actually clicking new instance within your cloud provider, and I've got Amazon, I've got Google. I believe someone was supposed to contribute the Azure ones. I have to double check on that. To installing CUDA, to installing the NVIDIA drivers, to installing cuDNN, right, which is what TensorFlow actually uses. cuDNN is a library on top of CUDA that is, has a lot of these convolutions and these neural network concepts, right? So it's a higher level library that's used directly by TensorFlow, and it hides you from the complexity of CUDA, which is very wonky and complex, and very low level in terms of memory management and things like that. So if you've ever tried to set up a GPU, the happiest moment of your life is this screen that you're seeing right here, that particular image where it has the NVIDIA SMI, tells you everything's working. The things to highlight here are the type of GPU that we have. This is a K80, so it's a pretty good one. We have 12 gigs of RAM. This is something else, sort of in the middle there, and there's 0 allocated right now out of 12, so that's good. GPU utilization, looks like I was just doing something and caught it right at 100. This is usually hovering around 0. And the other thing I like to keep an eye on is kind of on the left, in the middle, is the temperature. That's, that thing, why I like temperature is because when that thing goes up, I know it's actually doing something. Sometimes I don't, these like operations happen so quickly that you don't really see the GPU utilization go up. It might blip for like a split second, or it's 0.1 like utilized. But when that temperature goes up, that thing goes up very, very quickly and goes down very slowly. So, yeah, that's a good indicator. Getting GPUs to work inside of Docker was a huge pain in the butt until about 9 months ago. The NVIDIA guys recognized this, that Docker is a very common deployment, that in order to get GPUs to work with Kubernetes and with Mesos, they needed to support poking a hole through the Docker container and getting access to the GPUs. And that's exactly what this NVIDIA-Docker is. It's essentially a drop-in replacement for just running Docker itself. But so it's actually wrapping Docker, and it's exposing the GPUs as devices. Think of just like a drive mount or something. But now anything running within the Docker container, there's now a hole that's been poked out to the system to get to the GPUs. Okay. So if you just Google, right, the NVIDIA-Docker, you'll see it in action. Finally, as of Kubernetes 1.7, and I just got this working myself just a couple weeks ago on a beta version of Kubernetes 1.7, there is support for these GPUs. So this gives you the ability to tag a node within your Kubernetes cluster and say this node is a GPU-enabled node. And when I go to schedule work, that is going to be GPU work, like either a training process or running TensorFlow serving on a GPU, then Kubernetes knows to spin up the Docker container on that physical instance, because it does contain those GPUs that my Docker container is looking for. So yeah, just check out PipelineAI. There's a bunch of links, and you can follow the setup instructions yourself. Okay, GPU half precision support. I kind of referenced this a little bit earlier. When you're typically training, these GPUs have FP32 cores. They have, what in this chart is called single precision. A lot of people call it full precision. Is 32 bits. So you can represent a float using 32 bits. And these cores are optimized for floating point 32 operations. I mentioned earlier that if you can get through your data, your training data faster and validate your model quicker in half the time, like this is a huge differentiator for your company. This is huge benefits because now you can experiment twice as fast. And so people started playing with floating point 16, which is half precision. So you're losing precision because you have half the number of bits. Like what you can do is now put two floating point 16s inside of one floating point 32 core, right? And these GPUs have 4,000, 5,000 of these cores, right? It's different than CPUs that have 4, 8, or 32, whatever. Each of these cores can now actually operate on two floating point 16s, the same instruction, and on those two floating point 16s. And so like essentially you can get twice the throughput. And so here's some of the numbers here. If you see single precision, which also known as full precision FP32, you get 10.6 teraflop. On half precision, you get double. So this is exactly the kind of thing that we're looking for. Now, one thing you can do, because there's a bit of question, of course, as to how accurate is my model at the end. Because we're packing in so much data, the accuracy doesn't suffer that much. Now, it's kind of mileage may vary sort of thing. So, but what you can get a sense of is because you can get through the data faster, you can see relatively, did these hyperparameter changes or did this architecture change actually make a difference? And then once you're actually comfortable, during the experimentation phase, now you can back off and do floating point 32 and train at full precision with those final hyperparameters that you found during the experimentation. So that's one way to do it. I actually see quite a few people that just keep it at the floating point 16. There's also people that train at full FP32, which takes twice as long, but they're comfortable with that. They can scale horizontally. They, have enough cache, whatever. And then at the very end, take the model and quantize it down to 8-bit, which is one of those post-training optimization techniques that we talk about 2/3 of the way in to this talk. Real quick, I was just at the GPU Tech Conference earlier. I believe it was in April, I think, May of this year. So they had announced the Volta V100. Oh, and I should probably mention, I'm just going to go back a slide. I should probably mention the numbers here. The P100 are actually not the GPUs that we're using. So today we won't be doing floating point 16. We're on a K80, which actually isn't even represented here. I just realized it's the K40. K80 is the next generation. But the P100 is the chip that came out last year, 2016. And the newer one is now the Volta V100. And I'm going to talk about that in a sec. So the P100s, people, I think Google is going to have them soon. I heard Amazon will be offering them soon as well too, which is kind of unfortunate because the V100 is coming out. So who knows? Maybe they'll just jump right to the V100s. I doubt it, but so the V100, which was announced at this year's GPU Tech Conference, P100 was last April or May. This V100 is coming out later this year. It's not out yet for public consumption. It's got more GPU cores, more floating point 32 cores. And it also has 600 of these new tensor cores. And if you've heard of the Google TPUs, the tensor processing units, these things, yes, everyone loves talking about TPUs. We're all very curious. Google's only told us a little bit about them. There's a paper that was released recently that goes into much more detail. The first generation TPUs, so this is Google's version, were optimized for the forward propagation, so for the inference or for the scoring, right? The second generation TPUs, which are the ones that if you're a Google Cloud ML customer, you will get access to, are actually good for both the backpropagation, so the training side of things, and the forward propagation. These tensor cores now by the NVIDIA folks appear to actually be used for both. I actually haven't gotten confirmation yet, and I've definitely not been able to test them because I don't have access to these new tensor cores or this new V100. But they're definitely going to benefit on the forward prop. There's still a bit of a question as to how they could benefit on the training side of things. So actually here, and then, yeah, the other cool thing about these tensor cores is that they can do mixed floating point 16 and 32 precision operations. So before, you either had to pack in, two floating point 16s and can only operate between floating point 16s or just operate all, floating point 32. But yeah, here's an example where you have two floating point 16s that are being multiplied by something at full precision and then summing with with an FP32. So it's essentially thunking it, I guess was the old term, right? And then converting to, so you start with floating point 16s and you can eventually get to a floating point 32 results, which is really cool. V100, more shared memory. Shared memory is key on these GPUs. And with GPU CUDA programming, you're constantly, relying on shared memory to communicate between threads, things like that. There's thousands of threads concurrently running through here. There's a L0 instruction cache, so this is as close to the registers as possible. Faster L1 data cache. So if you recall, with these type of hardware caches, there's typically the instruction cache and there's a data cache. And data cache is what most people talk about when they are discussing the specs on a CPU, for example. How much L1, L2, L3. But it's important to note that they have a new L0 instruction cache to actually store the instructions as well, close to the registers. Faster L1 data cache, and here's just some quick performance. So obviously inference throughput goes way up with the V100 because of these tensor cores, but then also training is 12 times the teraflops of the P100. So if we go back and look at the P100's teraflops, so it would be 12 times that 21 right there at half precision, or 12 times the 10 at full FP32 precision. And that's not just because of the number of cores, but also because of these caching improvements and the tensor cores as well. One quick note about CUDA, and so Riley, just to give you guys context here, I'm talking about these constructs because they do come up later with TensorFlow. Yes, I realize this seems kind of off topic a little bit, but these are important concepts to understand because TensorFlow takes advantage of these things. This CUDA9 stuff is not out yet, so it's not this specifically, but you are sure that, once this is available, TensorFlow will be taking advantage of this. So just want to give you guys a heads up that CUDA programming typically is pretty barbaric, and it's kind of single instruction, multiple thread. So, there's all these threads coming in. So you see the P100 here. If there's an if statement in your CUDA code, and this is something, if you're doing a CUDA code review anytime soon, or if you've done one in the past, this is something you definitely pay attention to. If you see if statements, this is really bad. This is called divergence. What happens on the current P100, which is the latest that the public has access to, if there's an if statement, half of these threads, and let's say it's split 50-50, half of these threads or these cores go unutilized. So you're right away, you have 50% utilization. There's no way to sort of yield and let some other threads come in and take advantage of these cores being down or being underutilized. In cuDNN, there's more fine-grained, similar to CPU, more fine-grained thread synchronization and yielding semantics. So now you can actually, so in the like V100, you can see where there's some like yielding going on here, and you can more efficiently kind of like interleave different operations and free up those idle GPU cores to do other work. Okay. And this new architecture with the V100 and CUDA9, it's still optimized for same instruction, multiple threads. So it will always schedule things together that have that show similar types of behavior. The branch predictions and things like that can group like similar workloads, onto these blocks of threads, right? So these GPUs deal in what's called warps, which are groupings of 32 threads, and warps operate on blocks, and there's grids and some other sort of taxonomy with the way that these GPUs work. And so the scheduler is now aware, has always been aware of those, but now can also take into account an explicit yield, right, which didn't used to exist. So you see in the bottom right there, there's a way to, there's explicit like synchronization and yielding operations within CUDA9 that did not exist in CUDA 8. Quick view of CUDA programming. This slide should actually be before that other slide, but it's pretty barbaric. You must know the underlying hardware very well. You have to know bus speeds and really understand these tricks that CUDA developers know. They're so invaluable, right? The ability to pin memory, for example. This is a way to tell CUDA that you are going to use this memory later on. So keep it. So don't swap it to disk. For example, treat it special. Just give me a little bit more time, and I'm going to use this memory, kind of thing. So that's called pinning memory. So there's a lot of really low-level techniques that these CUDA people know. One challenge with CUDA programming, because the NVIDIA folks own the hardware and they own the libraries, CUDA, cuDNN, cuBLAS, right, which is a basic linear algebra subsystem for CUDA, right? And because so many people use these libraries, specifically TensorFlow, it's not uncommon. It's not super common, but it has definitely happened where from one architecture, one physical hardware architecture, so for example, from the P100 to the V100, or from the K80, which is what we're using, to the P100, the hardware has changed so much so that these tricks and cool little things that you were doing to work around the hardware limitations and the lack of explicit thread scheduling, these tricks that you used in a previous version of the hardware now don't apply to the newer version, or either don't have any benefit, or they could actually make the code slower because you kind of want to let the hardware or the hardware heuristics kick in and things like that. So and they're pretty good about being able to compile your old code. So CUDA9, for example, will still be able to compile for CUDA 8 code. The problem is if there's any mismatches, or the CUDA9 compiler will do its best to at least get it to compile and to run. It's going to put in shims, and it's going to try to do just-in-time compiling and possibly get you close, but it's obviously not going to be optimized for that new hardware. So just keep that in mind. Like a lot of people have given Amazon crap for not staying totally up to date on their GPUs, and the reality is, once if you're writing really optimized code for your GPU, which is what a lot of people have to do, to really get the performance gains. Switching hardware is just not an option, right? So it's almost better to just stay on an older version with your optimized code than to try to update and like rewrite all your code. Okay. So CUDA streams, this is also heavily used by TensorFlow. So CUDA streams came out in about CUDA 5 or 6, I believe. What's happening here is in the old days, before CUDA streams, this term streams is like a bit overloaded, but here it kind of follows the computer science-y like definition where, so I'll explain the problem, which was before streams, if a GPU is currently operating and calculating and doing GPU stuff, it was unable to trigger data loading in the background, sort of asynchronously pulling data in and asynchronously, pushing the results back. So it was essentially a sequential, non-interleaved way to, so first it would sit idle while data was being transferred, then it would operate on the data, it would do the matrix multiplies, whatever it has to do, then it would sit idle while the data transferred back. And this, so you were, at best, like you could get GPU utilization, maybe 20%, like, 30%, something like that, based on the amount of just pure, and it's transferring memory from the CPU, which has tons of memory, right? And it's doing simple tasks and, sort of controller tasks, right? The C and the CPU. And then it then hands over the complex data, the compute heavy data, to the GPU to do its primary task of just these numerical calculations. But there was just a lot of wasted. And so CUDA streams has the ability to, in the background, transfer. So while the GPU is operating on the current batch of data, think of a mini batch of data coming in from your TensorFlow training. At the same time, there's the next batch has been prepared. Maybe images were cropped or whatever, backgrounds, was grayscaled or something like that. That new data, those new JPEGs are now being shipped across while the GPU is currently operating. So the second the GPU is done, it then sends the results back in an asynchronous manner, and the next batch is there waiting. And so the GPU just has to pause to like kick off the async transfer back to the CPU from the current batch, and then it's able to start operating on the next batch. So this is very powerful. We actually have a direct example that we'll run through. We have a quick CUDA example that'll show very clearly this performance gain. Okay, so do that here. Okay, do that. Let's go to Explore GPU. This is why we're here. So I'm going to zoom in a little bit. We want to be on Explore GPU, this guy. Try to shrink that as much as I can. It's not shrinking anymore, so we'll do that. But Explore GPU 1A. There's the happiest moment of our lives right here. Zoom out a little bit. So it's just a quick sanity check. Make sure if you're not seeing this, yeah, look at that temperature. Keep an eye on that thing. Also, let's do another one here. This is an XLA one. Just as long as it says ran 2 tests, this is more of a sanity check. I'm going to explain this more later, but this is just running through and making sure that we got put on an instance within Google, or if you're running this within Amazon, like you want to make sure that the instance that you've been placed on, because sometimes you're placed on older hardware, and the XLA stuff takes advantage of some of the newer hardware and things like that. So just as long as that ran, that's good. And that'll save us a lot of pain later if we find that out early. So let's take a quick look. So here's some CUDA code. You guys probably weren't expecting this, but got little surprises for you here and there. So all this is doing, just a quick, so here's the main method. This should remind you guys of high school C or 8th grade C, whenever you learned it. So here we're just going to malloc. Oh, so the use case here is we're going to create 2 arrays on our CPU, which has tons of memory. We're then going to transfer the arrays to the GPU. We're going to have the GPU add them using a GPU kernel, which is just a fancy way of saying a function. That kernel then executes on the GPU itself, does the adding, and then transfers that result back to us. Okay, so we actually allocate 3. So if you see H is the host, D is the device. Host is a CPU, always. Host is always CPU. D is device. In this case, device is our GPU. This is just convention, CUDA convention, right? So the host is hosting devices, could be many devices. In our case, we have a single GPU. What we're doing is actually allocating 3 of these byte arrays, enough for the A for the first array, enough for the second array, and enough for the result. So C is the result. What's this ref H? I think ref H we use to compare later on, make sure that the values are the same, I think. So you'll see here some interesting, so here's where we're just generating test arrays. That's just the boilerplate random generator function that I define up on top. Here we're doing CUDA malloc on the device. So this is, if you see CUDA malloc, that there should be a D, something with a D here. CUDA malloc B, so we're creating the 2 arrays that we will in a second be transferring the generated test arrays from our CPU. Here we're allocating another, this is the result, so that's C on the device. And here we're copying from the device. Oh, so this is memcopy host to device. Yeah, this API is confusing. It's CUDA memcopy, so it's just like a regular memcopy. The order D and H are confusing. So what you have to look at is CUDA memcopy host to device. So it's not entirely intuitive what's happening there. This check error util, in CUDA, you're constantly in fear of errors. It's, defensive programming, worst practices. So it's literally if there's any error that happens, it's just going to crap out the program. It's not going to continue. So you'll see this boilerplate. This is just another boilerplate method defined up above. Okay, this is where these goofy concepts of GPU blocks and grids come into play. Don't worry too much about that. It's just kind of a grouping, taxonomy kind of thing that the GPU understands. Here is, so this is one modification. So this is all standard C++, 2011, whatever. There's one small modification that these guys have made. They have overloaded the less than, less than, greater than, greater than, greater than. And this is essentially clues you in that this is a CUDA kernel. Okay, so this is a kernel function. So I should, if I search, and I'm going to scroll up here, I should see a method called that somewhere. I always skip right over it. Here it is. So that's the exact same function. This underscore underscore global also, this is one of these C macros that essentially indicates that this is going to be a kernel. And yeah, these are the parameters being passed in. All this is doing is just adding A and B, putting it in C in an element-wise fashion. Yeah, ultimately by thread ID. And so let's go back and see. Okay. So this is invoking that function. So at this point, that function starts. Our program attempts to continue on, but it can't continue until we synchronize on the entire device, which makes sure, this is like essentially saying, make sure the kernel that I just executed has run to completion, and I can now get the result back from the device to the host. So from the GPU down to the CPU. So essentially things block here until that calculation is done. You can only get the very last error from CUDA. So you have to check for just the get last error. It's a bit barbaric. And now, so we first synchronize that. And so we block here until that calculation's done. We check any errors. And then now we actually copy from device to the host, okay? And C is the result. And then we're just going to compare and make sure that what was calculated on the CPU and what was calculated on the GPU are the same. Make sure there's no funny business. And then we just free everything up. CUDA free, that's freeing up the device for being good citizens. We're freeing up what's in the CPU. It's not really needed. Once this program dies, all this stuff gets cleared out anyway. And we also, this is really good to call CUDA reset, this device reset. Return it to a state as though there was nothing ever done on the GPU. And that's just, just to clear out some extra things, make sure memory's truly been freed and there's no like remnant of this program anywhere on that GPU. Okay. So we can actually run this. All right, took about 474 milliseconds. You can see, you can kind of read some of these. Allocated, double the amounts, 2 of the byte arrays. Allocated the 3rd byte array to store the results. And it's doing the copying, it's doing the summing, and it's bringing it back. And now it's freeing up the total of this and this for all 3 of those arrays. It's freeing those up in the GPU and cleaning itself up. So let's actually run this a couple times just to get an idea of the performance. 464, I don't think it ever gets below 450, usually 470, 466. Okay. Also keep in mind when you're dealing with GPUs and if you're particularly sensitive about performance and performance benchmarks and doing things like that, make sure you have hit all of your GPUs. If you have a 16 GPU box, a single node with 16 GPUs, make sure your TensorFlow code has done one run on all 16 of those GPUs. If not, the first time a GPU gets allocated TensorFlow code, the GPU has to generate what's called PTX, right? Which is their version. It's the GPU ISA, or the instruction set architecture. So right, like essentially it's taking your code and then compiling it for the GPU. So similar to how right, like the Intel chip would take your code and then generate assembly, right? It's like the GPU assembly language. So this bites a lot of people because they see the first run through, especially when they're doing heavy performance testing, and they don't always hit every single GPU. In fact, TensorFlow will very often on a multi-GPU machine, it will very often just choose one GPU to do all of the calculations. And it's not always the case. It's obviously going to use heuristics and see, if everything can be fit into one GPU, it'll definitely use the one GPU. If you explicitly do assign all, 16 GPUs, then of course it's going to use all GPUs. But TensorFlow, if you don't specify which devices to use, it will always choose GPU over a CPU, and it will typically just pick one GPU over multiple GPUs. And this is the classic, in any sort of distributed sense, this isn't distributed in terms of networking distributed, but this is distributed in, terms of like hardware. There's multiple GPUs that still have interconnects, and, those buses are like relatively slow, things like that. So if it's similar to if you, for example, had one Spark worker, right, that could do all of your work, then why do you need 15 others, right? All you're doing is imposing extra synchronization and network traffic and bus traffic, right, and things like that. So just keep that in mind, that if you're not careful and you haven't verified that you've hit all 16 GPUs, that you will see performance problems. As you start doing more and more load testing, you think you're using them, but you're really not. So yeah, that's a case where you would explicitly run it once and warm up, but that's kind of the term, like warm up each GPU and be certain that you've hit. And there's ways to turn on logging so that you could see where operations get placed, and you would just review those logs and make sure all 16 got hit. Okay, so the summary here is this is 466 milliseconds. And oh, I forgot to update this image. This is actually, you guys can kind of figure it out. So this terminal thing isn't the way to do it, but it's under File, New, and then do Terminal. And then you can go back here. Actually, let me change this on mine. This won't, I don't think this is worth us doing a big poll, but what we're trying to do is to just open up a terminal. This is the new way. New, and then go to terminal there. So the reason we have to bust out to the terminal is this particular script doesn't work very well running inside of a notebook. So one other cool thing about Jupyter Lab is that it lets you have multiple tabs side by side. So what I've done here is I'm using the Linux watch commands, and I'm saying this is the interval, it's every 1 second. Right, like execute this command, which is our favorite, kind of checkpoint for we've successfully installed CUDA and the CUDA toolkit. What we're going to do here is rerun this same thing 10 times, and let's keep an eye over here. We should see memory blip. We're going to see temperature go up. See, that's my favorite. That thing's definitely doing stuff. We should see utilization. Let me make this a little bit bigger. And you can jack this. I mean, I wouldn't really go above 10, but I'm going to be crazy and do 50 and just kind of see what happens here. Sometimes the GPU gets wedged. Yeah, so you saw a blip there, 9%. Some of the memory going in and out, 60 megs there being allocated, 3 megs being allocated, and temperatures are rising. So I think the highest I ever got, maybe 57 degrees Celsius or something like that. I was trying to burn it out one day, but it wasn't letting me do it. All right, so I'm actually going to stop it because I think if you do it 50 times, I think it runs. So I'm hitting the stop button here. And let's do, so this is the advanced CUDA code. This is with the streams. And let me just kind of minimize that guy over there. The key difference here is we're still doing CUDA malloc. The key difference is that we're now creating a stream, an explicit stream. And so instead of doing a memcopy, now we're doing an async memcopy, push to device. So this part's the same, but it's async, and we're doing it on a stream. So we're doing it in the context of a stream. So before we were just doing it on the whole context was the device, which is what we had to synchronize on later. So now check this out. So we're memcopying on the stream, memcopy on the stream. That's A and B. Let's see, where did C go here? Why didn't we have to do, oh, here's the malloc. Okay, right. So the malloc stuff stayed the same. So we allocated A, we allocated B, we allocated C, and then here we're just copying the randomly generated A, randomly generated B, async through a stream. And then now we're going to use that same kernel. It's the exact same code. It's just because we're now dealing with this stream, right? So we're synchronizing. So once that calculation is done, not synchronizing on the whole device, which there could be other streams operating by other users, by like other processes, things like that. Now we're going to do an async back from device to host. So what this is like essentially doing is, as data is coming in, it can get operated on, and the results, because this is such a simple kernel, right? I'll show you guys the kernel again. It's the exact same code. Yeah, so nothing here changed. As data is coming in, being calculated, it can then start to asynchronously get streamed back. Because we're synchronizing on the stream and not the whole device, this is possible. Async, comparing, all this is the same, CUDA free, freeing, device resets, be a good citizen. So let's run this. Okay, so even a single run, the GPU is already warmed up, so we're not worried about that. But even a single run is, what, about 100 milliseconds faster? And, you know, we could do this 50 times. Over here, take a look. Check out the temperature, check things out there. So, yeah, so one thing here is that I'm actually we're doing a watch every 1 second. If we change this interval to 0.5, we might be able to catch the utilization blips a little bit more. Yeah, this is blipping a little bit more now. I wouldn't go too much lower than 0.5. Maybe you could do 0.25, something like that. But at some point, it gets starts to complain a little bit. Oh, actually, that finished. So let me run it again. Okay, but our trusty temperature is getting up there, and that's what we like to see. Okay, so I'm going to kill that. And I'm actually going to kill this cell because I don't want to really do 50. One sec here. Okay. Oh, and then there's one more thing that you guys should know, and then we'll take a quick break here. Numba. Numba, if you're not familiar, this is a library out of the Anaconda guys. If you're not familiar with Anaconda, they're totally badass. If you catch any of their talks, they're just incredible guys. They actually have a couple of contributors on the Jupyter Lab project here, so they're pushing things forward. Yes, Anaconda is it's a scientific computing Python-based company. They do a lot with like Dask and distributed Python, and have a lot of ways to tweak performance of Python. So one of the libraries that they came out with is called Numba, and it's essentially a drop-in replacement for NumPy. And if you're familiar with SciPy and NumPy, you'll know that you're never really running just Python code when you execute a NumPy method. You're really running a C compiled version of that method that's optimized for the hardware or for the operating system and the kernel, the Linux kernel that you're using. So that was one of the things when I first, I was a Java guy traditionally, Scala guy, C guy before. When I got into Python and I realized this about these libraries is that there's this project called Cython, for example, that you can compile your own Python stuff, right? So C is actually very, very much a part of the Python ecosystem. And as much as possible, people write the C versions of these libraries, right? And so you always want to make sure that you're using those. So if you take it one step further, these Conda guys, the Anaconda guys, have actually instead of compiling down to Intel assembly, they're actually taking the Python function, compiling a GPU kernel. So similar to that kernel I was showing back here for the sum arrays, the simple one. They've gone ahead and implemented the GPU equivalents, and which then get compiled into the PTX and like all that stuff specific to the NVIDIA GPUs. So if you're ever at the GPU Tech Conference, it's one of my favorite conferences. These guys are all over it. They do workshops, they do everything. Sign up for it early because they all get sold out. And so here's some cool stuff. So if you just think of it just like you're running like NumPy methods and functions, but it's actually like you'll be doing it on Numba itself and on the GPU. So I actually snagged this. This is all open source and everything. So I snagged it from those guys. I'm not going to spend too much time on it because there's a lot of comments in here. This is actually from one of the workshops, but this is like definitely out there. It's off the pipeline/gpu.ml project within GitHub. You can actually, these Python notebooks render perfectly inside of GitHub, so you don't even have to have a running server, like Jupyter server. You can just look at them right inside GitHub. So there's cool things here. You could say CUDA JIT and say device is true. Device again is our GPU. So yeah, Numba has this module called CUDA that you can tell it, hint and say, hey, try to convert this and make it so just in time create a CUDA kernel. So this is really powerful. This is doing its best, the best that it can based on primitives, like the math libraries and the operators and the like multiply, sign, and that kind of stuff here, and do what you can to try to make this GPU enabled. You'll even see, let's see, here's they're accessing the device. Oh, this is actually moving memory to a device. The CUDA module includes a function that will copy host to the GPU and return a CUDA device array. So this is similar to that memcopy host to device. Very simple Python version of it. Device array. So this is doing just a malloc. Here we're doing it from the device, copying back to the host. So here's that exact same add kernel, except written in Python. So before I had it written in C. If you don't want to use C, but you still want to make this a CUDA kernel, this is going to do it for you. So you do it in your nice familiar Python, and all you do then is call this add kernel, which has been decorated with this CUDA JIT. And this is how, so the unusual sort of calling is designed to mimic those CUDA, right. So they, in Python, they're doing it this way. Like this is the operator overload, or the symbol overload here is bracket bracket, which is non-standard, but it's similar to this goofy thing that we saw in the C stuff. So one other thing, here's the kernel synchronization. So force async, force sync after. This is device level synchronization, right? Here it's saying take a look at CUDA streams. If you want to run multiple kernels on a GPU in parallel, take a look at CUDA streams. Otherwise, we're synchronizing on the entire device itself, which is not good. Okay, here's some shared memory stuff, and I think that's it. Yeah, I think this notebook runs completely. There was one issue with it. I think I had fixed at one point, but if not, it's not going to hold anything up here. So, okay, I'm going to jump back here, and then I think my throat needs about a 10-minute break. So break time here. If you have questions, please throw them in there into the chat. Anything before the break? Any questions that you guys have? Let me, this is what we're going to cover after. So don't worry about, we've covered quite a bit already. We've covered the basics of how TensorFlow uses GPUs and CUDA, and now we're actually going to get into TensorFlow, and we're going to move pretty quickly. I think we have about 30 slides left or something like that, so we will move quickly. I'm going to check the chat for any last minute. Oregon. Okay, Bernie has an issue. I used the password Edge, but wouldn't work on Firefox or Chrome. Okay, so yeah, browser issue. I use Chrome. I haven't heard anyone else complain about Firefox, but yeah, man, whatever works for you, just as long as you can move ahead. And this is what we're going to cover. So the next couple of sections are going to be more training optimizations, and then right at this part that says AOT, from that point on is going to be runtime optimizations and post-training optimizations. Cool. So I'm going to put you mofos on mute and be back. Actually, what time is it? Actually, let's do 10:30. So 15-minute break. If you guys want to run through some of the notebooks and things like that, be careful with GPUs. You will have an issue about notebook 3 or 4 where you start to run out of memory. It might not be totally obvious that you've run out of memory, but what the workaround, and I put this in the notebooks, usually where it happens is to just go into the running tab, which is going to be over here. Go into the running tab and just kill. Yeah, probably want to kill the terminal too, also. So, okay, I'll see you guys at 10:30. Throw any questions into the thing there. All right. It is 10:30. Oh, yeah, sorry, yeah, most of you guys are on the East Coast, so 1:30. Okay, looks like one person's still having problems with, hang on a sec here, let me share. Okay. If there's anyone still having problems, I think the issue was with the terminal. Yeah, one second, let me make sure I'm addressing the exact issue. Okay, Bernie, I went back to Chrome. I don't have a % prompt in the terminal. Okay, so Bernie, just to confirm, you're doing this. You're doing new. You get a launcher, and then you're just double clicking or clicking on. But you're not seeing this. Do you see this, Bernie? If not, there's you can actually revert back to classic mode. Classic Jupyter Notebook. And you could do that. Yeah, I mean, maybe you could try to do start new console here. You won't be too crippled by not being able to run the console, by the way. And for those steps, you can just kind of follow along. But if you go into commands over here, launch your classic notebook, that'll actually go back to the old way. So give that a try. And then at this point, I have to keep moving ahead. So go back to the new Jupyter Lab. Yeah, so again, in case you're looking, you would click on commands and launch classic mode, boom, right there. Someone asked about Numba reference. You just got to Google it or go to the Anaconda website. There's a lot of documentation on it. There's a lot of flexibility. You can do your own, yeah, like you can either do the JIT compiling, or I think you can even build your own, right, like adapters for your specific operations to generate the kernels for the GPU. Okay, so let's go back here and make sure I'm sharing this. All right, so we're going to talk about training and even debugging. You can do kind of a live debug. It's kind of cool. It's one of the more sophisticated debuggers I've ever seen. It takes, you know, command line debugging to the next level. You can use a mouse and everything. I'll show, that's actually one of the notebooks. You can play around with it. So training and debugging a model. I mentioned this is not intro material, but I do want to cover, and yeah, I apologize for the graininess of that image. I kept making it bigger and bigger, and I didn't go back and actually resample it and get a cleaner, crisper image. But I do want to cover some core TensorFlow terminology that is going to take you a long way once you understand the terms that are used inside the code, the TensorFlow code, inside the TensorFlow documentation, and also outside of TensorFlow and in, you know, kind of the academic world, okay? There's a couple key concepts here that are very good to understand. So obviously, first of all, tensors, just think of these as n-dimensional arrays and ignore the academic sounding way version of the term. Just think of all the things that we know, scalars, vectors, matrices, these are all forms of tensors, okay? tensors are flowing. You see in the block on the right side in that diagram. I kind of, in the diagram, the hyphens at the top are sort of the actor, you know, who's actually doing what's the action below it. So TensorFlow is flowing tensors. Let's see, operations, you know, there's matrix multiply, there's add. These are the, so these are the more obvious ones. These are the numerical ones. Now we have, but as I'll show you guys here in a bit, when we train and, you know, the output of training generates this gigantic graph that has summary loggers and, you know, ways. I think I had mentioned TensorBoard, or we verified TensorBoard works. We're going to use it here in a sec. During training, you can instrument your code to write out every, you know, 100 steps or every hour, right? The value of your loss function, for example, right? Like, where is my current, what is the value right now? And what you want to see is you're always trying to minimize loss, right? The way that these models are typically trained, you're trying to optimize and get loss as close to zero as possible. So you start off with sort of random guesses for the things you're training. In our case, we're training in that lower left of the diagram. We're choosing to train B and W. So just, you know, a normal y equals mx plus b, you have B and W are what you're learning, right? Bias and the weights. And so during training, there's a lot of extra nodes that are introduced, you know, and there's a lot of internal assertion nodes that are inserted, like check numerics is one, you know, make sure we haven't gone completely to zero, and, you know, certain things that make sense at training time. And all of that stuff's going to get stripped out. So that's going to come in about 2/3 in, where we'll strip all that stuff out because it's not needed when we go to deploy. So TensorFlow operations are in purple. TensorFlow is performing those operations. This whole thing is a graph, similar to Spark. It's a directed acyclic graph. These things all connect to each other in some manner, or else they wouldn't be part of this graph. And a session, which is shown, I think, on the next slide. A session is what you as the developer, the data scientist, open up or create, you know, a session to even define these graphs. It's exactly the same as a Spark session. You know, you would open a session, you would eventually want to close the session. A session can actually contain more than one graph, and this is fairly common when you're dealing with larger pipelines. So if you think, if you're able to step back and, you know, think of Spark as an ETL graph and TensorFlow as the neural network graph, right? And if you can almost conceptually put those together, what's starting to happen is, you know, Spark Summit happened recently. They made some announcements where they're starting to support TensorFlow, and you know, it's really packed together right now. But Spark is trying to become more like TensorFlow, and TensorFlow now is starting to introduce queues and dataset APIs and more ETL type. That's where some of the HDFS support came from, right? These are obvious signs that Google realizes that they need, you know, that having just a simple, or not simple, but having a focused, like, numerical, right, like, subsystem is a bit useless if you can't, you know, transform your features and you know, do all of that stuff for the training data that's coming into these training graphs. Okay, so we'll talk a little bit later about queues and you know, shuffling and the ability to crop images, and, you know, these are all part of overall pipelines, right? So in reality, you typically will have multiple graphs within a session, one session. And yeah, also keep in mind, when you're training on these images and you're cropping them and, you know, turning them and inverting colors and grayscaling, a lot of those things have to happen to the data that's coming in raw from the outside during scoring time, right? So when you're first playing with the toy examples, you don't really realize that, but the second that if you try to pass in an unaltered image, into your network that has been trained on cropped images, this could potentially lead to very poor results, and it's not, so you will want to carry over some of that pipelining, the feature transforming into your on the prediction side as well. Okay, these next two, feeds and fetches, these were difficult for me to really grok until I finally was talking to someone, or it just clicked. So this term feed, when you have so you've built up this graph, you're learning your B and W, so those are your variables, or sometimes called weights or parameters. The whole point is those weights get learned on a set of inputs and a well-known label or output, right? So an X and a Y, for example. So you feed in X, you feed in what the known answer is, the answer key for X. You then run it through the network. The actual result comes out of the add operation, okay? And that's what's called a fetch. And during training time, you're comparing the fetch, which is the output of the X going through by itself, to the known value, which is Y, which is part of the training data. And that's what you figure out the loss or your error. You would then back propagate that, and you would make a change to B based on how much it contributed to the loss, and you would make a change on W based on how much W contributed to the loss on that particular run through the network. So feeds and fetches, these terms come up a lot. I fought these terms tooth and nail until I finally just got used to it. It's in all the documentation, and it's fine. It finally makes sense. So when you build a graph, there's one concept that's actually not listed here. I think I just ran out of room, or I didn't find it valuable at the time, but I think it is valuable. The graph itself has a placeholder, and that's physically what the name of the construct is in TensorFlow. So you feed data into a placeholder, and you fetch data from an operation. And so that's what was always confusing to me, was the fetch side of things as well. So just keep that in mind. And typically when you're writing code, you are building up your graph with placeholders, variables, and obviously tensors, operations, and that's pretty much it. You can do quite a bit with just those few things. Okay, and then that placeholder is static, but it becomes dynamic when you feed it data. All right, and at the end of this, you will have trained weights. So that's those variables. TensorFlow code uses variables for the term. They're often called weights or parameters, sort of legacy AI terms, neural network terms. And device is another term here. Probably what I'll do is replace device with placeholder, because I talk about device here in a sec. But device is just like we've been calling it before, right? Like CPU, GPU devices. And you can explicitly, so in Python, you could do that with statement and essentially, defining a scope. So you could say with TF device. This particular case is kind of an advanced case. This is two different worker nodes with one GPU each. So this is actually how you would specify distributed. Okay, and it would be up to TensorFlow to decide, or if you want to go even one layer deeper, you could say you could specifically assign just a single worker. Okay, so those are kind of the key constructs. The key here being feeds and fetches. You always fetch from an operation, and you always feed into a placeholder. All right, so here's more on devices. So if you are doing code reviews or trying to learn from samples, things like that, you'll see with TF device and CPU 0. When you say CPU 0, you're actually saying all of the CPUs. there's really not much benefit. You can technically target a specific CPU. I haven't seen it much in real production systems. People just usually do :0 and let the CPU scheduler figure it out. The GPU scheduler, or for like GPUs, this is where you could potentially choose to target specific GPUs. And in the case of a 16 GPU, like I said, you would want to warm up, have kind of a pre-training phase that hits all 16 GPUs. So that's where you'd say with GPU 0, GPU 1, GPU up to 15. And like I said, TensorFlow usually prefers a single GPU to reduce the amount of inter-GPU communication and just sort of overall communication. But, yes, just like Spark, if you had 1 worker versus 15 workers. The other thing that right now is experimental. We have some pretty good like examples of it that actually work. This XLA stuff has actually come along quite a bit in the last couple of releases, so I think this will become the default here pretty soon, probably definitely by the end of the year, I'm thinking. But you can actually say with TF device and then give it XLA underscore CPU or XLA underscore GPU 0 through N. And what you're doing is hinting to TensorFlow to try so not only place it on this specific device or on all the CPUs, but try to JIT compile, right? And so as it's seeing instructions coming through and it's executing, it can see that we're always doing this add operation after this matrix multiply. So why don't we just fuse it together, right? And it will use so in Spark, for example, it's using properties of map and filter and can like fuse those together. And TensorFlow is doing something similar with properties of like addition, multiplication, things like that, and like linear algebra. One thing I should point out here, and I have another slide on this later, but actually, yeah, I'll save it for a little bit because I have a full slide on it. Okay, more about our surroundings, training metrics. This is at training time, what's going on? So TensorBoard is the thing that can listen on those log summaries, right? Or those, I think they're called summary log is the operation that TensorFlow uses inside of the graph. So as you're training, like I said, every 100 steps or hour or whatever, you can choose to write out, there's the boilerplate code. What you do is, and yeah, it's called summary writer, and there's an operation called merge all that's essentially like kind of like a checkpoint thing where it's saying at this point, dump out all the values. And these get written into these event files. I have a buddy whose company actually, his whole business is based around parsing these event files and building a better version of TensorBoard that actually can pull in GPU metrics. And I'm working with him to extend it to support model serving metrics, right? So when that model's been deployed, so that you can match up how well did this model during training use this much memory, how is it doing out in production, it's using this much memory, or its predictive performance is this relative to another model that was trained differently. So kind of having one big dashboard like that is super useful. So TensorBoard, I feel, is one of the reasons TensorFlow has kind of taken off. I can kind of back up and give you some thoughts as to why Spark, for example, took off. It had a ton of examples right from the very get-go. It supported ML, it supported graph, and these type of libraries give, people who were traditionally just doing ETL with Hadoop, kind of gives them something interesting to pay attention to and to read about, and kind of makes advanced analytics more usable and more accessible, right? And TensorBoard, I feel, if you do it right, and unfortunately it does require code in, you to physically instrument your code. It's not usually this boilerplate, but yeah, we're using low-level TensorFlow here, higher level libraries like Keras, things like that. you can, there's easier constructs for this type of thing. But making anything more accessible is what VCs love. It's what, it's why people start companies. It's why technologies tend to take off, right? Is when they become accessible. And keep in mind that TensorBoard does not replace the need or doesn't fix the problem of neural networks being, like a black box and being mysterious, and the sort of inability to explain, which features are the most important, and all the, traditional things that have held neural networks back are not fixed by TensorBoard. But TensorBoard gives you sort of, while training is happening, some of the things people use TensorBoard for are they can validate their model, with a holdout data set. So they've been given, 100% of their data, so they've been given, like 100 items to train on. They're purposely holding 20 out that the training step never sees. The other 80 go into training, and after those weights have been learned, those variables have been learned, now you take the holdout 20, you run it through with those current values, and that's another metric, and that's your sort of validation or your test metric to see how well the model's doing on data it hasn't seen. Because when it is pushed out into production, it is not, it's going to be seeing data that it hasn't been trained on. And so what you can do for these long-running training jobs is you could continually be validating every day, right? So let's say these are 2-week training operations. Each day you could spin up a separate cluster, validate. You can then visually see, oh, my validation data or my validation results are showing that this model is actually not that good. It's not generalizing for data that it hasn't seen. It's starting to now overfit for the data, for the training, for the 80% training data that it has seen. So in that case, you would actually stop the training and save, your system resources, save your Amazon bill, cut the thing short after, you start noticing this, and don't run the full job to completion. So this is a very common pattern I'm seeing more and more of. I'll talk about this too in a bit, where you have a training cluster, and every, checkpoint, each day, every hour, some sort of interval, it's going to write out all of the latest variables that it's learned, which is the whole purpose of this training, is to learn, W and B in our specific case. By writing that out to HDFS, that then triggers a validation cluster to spin up, which has the holdout data, has that 20%, and then is validating while the training continues. So it's sort of optimistic, and you would continue training for the next day while you're running the validation, and then if the validation does come back negative or with poor results, then you would then halt the entire process and maybe tweak some hyperparameters, maybe change the architecture hyperparameter itself, change the way the nodes are laid out. Okay, so yeah, these like event files, and what you do is when you start up TensorBoard, you point it at a parent directory, and any runs which are defined, by the name of the, actually any run is essentially a subdirectory inside of that parent directory where you pointed TensorBoard to start. So you would initially point TensorBoard to an empty parent directory. You can now point TensorBoard to HDFS, which is really important, especially for when you're doing distributed training. Now, all of the workers in your cluster can be writing to the same HDFS location, and TensorBoard sees all of these and could merge all of these into one graph if they all share the same, share the same subdirectory. Then they would get rendered correctly inside the same chart. And TensorBoard lets you compare. And also, the other cool thing is you can look at that. So this diagram on the right that says graphs, TensorBoard graphs. So this is actually what our simple linear regression looks like inside of TensorFlow, the graph that we ended up building. And you'll see, for example, there's some that are in blue and some that are in green. This is an example, and I covered up the legends. Can't really see it, but green is green is the GPU, and blue is the CPU. So this common pattern that like we'll see like more and more is anything compute heavy, right? Like matrix multiply, we want to go to the GPU. So we would explicitly say with device GPU. And then all the other stuff, just storing the variables that we're learning. This is not something that we want the GPU to be doing. We want GPU's memory, which is very scarce, to be focused on, to be freed up for the intermediate calculations of the partial derivatives and some of the more complex things, and not be burdened with having to store large variables that we're trying to learn. Here they're very small variables, but when you're dealing with word embeddings and things like that, like you want the GPU to have as much memory as possible. Okay, this is one of those libraries I mentioned you can stick in at the end of your Spark or your Hadoop pipeline. And TensorFlow-Hadoop, it's this interesting project that popped up. I kind of found it by accident. I think I was Googling around it. It's a first-class citizen off of the TensorFlow parent repo, org repo, and it's called Ecosystem. And there's a lot of things in there. I haven't yet seen Kafka pop up, which is interesting. I'm kind of waiting or wondering if there's going to be any sort of Avro conversion tools or ways to continuously feed in data, in sort of the scikit partial fit concept, continuously feed data in from Kafka for training purposes, or even for the serving. So think of TensorFlow serving sort of running inside of a Kafka stream, or even a Spark streaming app, right? Like you could have Spark streaming out there is collecting data and then scoring with some sort of library that works with Java or Python, and then we could score that way. Okay. And then back on that last slide, there's support here for Kubernetes, Docker, Mesos, definitely HDFS. Okay, so I talked quite a bit about feed, and I think I burned that into your guys' heads. Feed is how you get data in for either training or for scoring. So the only difference there is at training time, you give it the answer, the actual score, and then training makes adjustments to the variables. Or for scoring, it's just the X, and it gets combined with the W, and then it gets combined with B, and then out comes the final result from the add operation. So feed dict is what you see in your toy examples. If you copy and paste code off of the TensorFlow site, you'll see lots of feed dict in there. It's the absolute slowest way to get data in to your graph, right? So in particular, when you have large data sets, tons of images that you're trying to train on, you don't want to be dealing with feed dict. Feed dict is kind of a nice way if you're just toying around with a small model and you want to create a NumPy array inside of your Python app or your Python notebook, and then just feed dict equals blah blah blah, and you just point it to the NumPy array. The problem with feed dict is it requires Python to C++ serialization, right? Like TensorFlow's core is all C++. Python is just literally a binding to get to the C++. Some of the tools that we're going to work with today are only in C++. Some of them actually are starting to get Python bindings to make this easier for data scientists to incorporate into their notebooks and things like that. But yeah, so instead of using feed dict, and then feed dict is also single-threaded. It's synchronous, so it kind of suffers that problem we were discussing with streams. It's just really slow. Has that problem where you're not fully saturating your CPUs, your GPUs. They're constantly idle, waiting for more data to come. So there's a couple things you can do. You can use queues, and you can use this new dataset API. one thing I do want to point out, there's an image down there on the bottom. This was something also I stumbled upon while putting together this workshop. Is there's this performance tab off of TensorFlow's site. And in particular, if you click on benchmarks, and while the benchmark results are, very interesting and obviously shows TensorFlow is the best and all that, so you can kind of scroll through all that and just assume that it's the best. At the very bottom, they're like, oh, by the way, these are the scripts that we use to create these benchmarks if you want to do them yourselves. And so this opened up a whole thing. When you start looking at their scripts, which are, Python scripts, you start realizing that they're not using feeddict, of course. They're also not even using queues in some cases. And suddenly you start seeing dataset and some weird API that we had never seen before. So this dataset API, and if you come from a Spark background, you probably get the shakes right about now because you were likely part of RDDs, and then you migrated to data frames, and then now you're being asked to migrate to dataset, and you don't quite know why because data frames work fine. And but for right now, they're calling them datasets. And this is where you start seeing TensorFlow becoming more like Spark. Okay, and the whole point here is to get data transformed and munged and combined, things like small file problems, like in HDFS, the traditional, you have tons of logs coming in, but they're single files, and you want to get them batched into larger blocks, which is obviously more efficient in terms of, disk seeking and, memory packing and all that kind of stuff. So, okay, so queues. This concept of a queue, it's more than just a traditional computer science queue, that we study and restudy during our interviews. This is more of a pipeline. So these queues can be chained together, and they're physically queues, and they have, queue capacities, and there's capacity planning, and there's, queue threads, and you could do multiple I/O in and out of these queues, right? Like based on thread pools. So one of their like obvious jobs is to pull data in from HDFS or from S3. But then you can very quickly create a queue whose compute job isn't to just do I/O, but now is to take an image and crop it, or take some CSV and parse it and extract certain features. One sort of obvious one that comes with TensorFlow itself, it's called the random shuffle queue. So because we're typically doing stochastic mini batch gradient, right, like descent, right? So the stochastic part is the random part. And because we're doing mini batches, so right, like when you're training with these neural networks, you never want to train on one single instance or one row of your data or one image, right? That's not helpful. Or right, like per batch, right? Like batch size should not be one. Ideally, you can train on the entire data set, right? And that's typically how, scikit-learn, like when you call fit, things like that. This is something Spark helps with, is you could treat, this whole data set. You could train on what appeared to be the whole data set, but really it's being partitioned into multiple workers across the cluster. So the problem is, if you're pulling in data off of disk and it has been put there in some order, what you don't want to happen is the network to learn that order, right? Like the network shouldn't be learning about the order if in fact the order doesn't matter, right? If it's time series, then of course the network should be learning the order, or should be preserving the order in which that data was written. But so there's this random shuffle queue, and that's the stochastic part of it. The mini batches is what these queues provide. You can specify the queue size, the batch size that the queue is going to provide you. And I'll talk about that here in a sec, about how to actually do the capacity planning. And then, stochastic mini batch gradient descent. And then of course, gradient descent is what's being used, right? That's the optimizer to try to minimize the loss, right? It's making small little steps towards what it's hoping is going to be the minimum, right? Because we're trying to minimize. So yes, I mentioned these queues can combine many small files into larger blocks, which in this case would be a TF record, which is TensorFlow's preferred file format. And you're typically, when you're building your queuing pipeline, you're typically using CPUs for this. And that's because at most what you're doing is shuffling, like cropping is very easy to do, grayscaling, very, very easy to do. Yes, any sort of dumb processing, including I/O, you should just throw a bunch of CPUs at it. Don't bother with the GPUs there. It's not really going to help you, just gonna, for the price. And also because CPUs have a whole ton of memory that they have access to, let the GPUs focus on cool GPU stuff and let the CPUs focus on the boring I/O and pre-processing. These queues naturally use CUDA streams. This is how they keep the GPUs saturated. And I don't have a whole lot, by the way, on the dataset API. I just backed up a couple slides. This just dropped. Haven't fully grokked it. I'm still a little bit wounded from being at Databricks and having to go through the migration of RDD to data frame to data sets with our customers. So forgive me for not having too much more on the dataset API. But backing up a couple slides again, there's an arrow off that performance tab. If you go to benchmarks, you can see a script and you can start to link to the code that way. Here's just kind of a visual data movement within the queues. So there's that random shuffle queue that starts with files, could be on HDFS, S3, Google File System, whatever. Doing some decoding, doing various things. The goal here, and because they're using streams, the next batch is immediately available to the GPU right when it's complete with the current batch that it's processing. Quick note on batch sizing for these queues. So someone actually just asked us yesterday at the PyData conference. They were having this problem. They couldn't figure out. So the batch size it is almost always limited by your GPU RAM. Okay, so assuming you have access to the whole GPU, which we all do today, you can take the total GPU RAM, which is about 12 gig currently. You would divide it by sort of the like average size of your JPEG. If you can calculate this, if this is easy to calculate or just get a rough idea. If you divide into the RAM, then this is going to give you sort of a back of the envelope batch size. So in this case, for example, we were able to pass in 64 JPEGs on average. And what you want to be careful of is that you don't undersize the batches because then you're basically starving the GPU, right? Like the GPU could be doing more in parallel. If you undersize it, you're now doing more transfers into the GPU, which with streams isn't that bad, but it's still more data transfer versus one batch being transferred. If you oversize it, now things don't fit into memory and there's some thrashing and it has to maintain partial batches. And, so this is where some of these statistics and seeing a dashboard, like being able to launch a job and have the data scientists go and look at some of this stuff, right? Like they don't have to necessarily understand the details of how these things were calculated, but if there was like a red, some sort of red indicator that was showing, batch size is too much or is too low, then it gives them the ability to turn a knob on their configuration for this pipeline and see how it changes. That's typically when they just want these jobs to finish quicker and stuff like that, these training jobs. Yeah, and so CPU threads, they're actually pulling the data that's limited by CPU cores, usually some multiplier. Similar to Spark, when people always ask how many workers do I need, how many partitions do I need, the general, when Spark first came out, it was typically 2 to 3 times the amount of total CPUs in your cluster. That was just kind of the back of the envelope. That was how many partitions you would want when you ran a job. Now that Spark has become faster, it's now more I/O bound. And what you want to do then is take a multiplier of 5, right? And then that way you're sort of saturating, and because you're now bound by I/O out to disk, what's happening is you can then interleave in more threads while threads are sitting back, or while the processing is halted, waiting for I/O. So typically, that number 5 is kind of a good number for like a lot of things, 5 times whatever the hardware resources you have. So here's one way, and this is actually starting to, so this is kind of a hokey way, and this was the original way to see how your GPUs are being utilized, where time is being spent. This is actually using the Google Web Tracing Framework, which is the WTF, which is kind of funny. It's a brute force way to instrument your code. So there's the boilerplate code inside of your training job. And that's going to write out in JSON in a format that this WTF tool, which was traditionally used to see where is time being spent on a web page and things like that. So they've really basically like reverse engineered that format, or complied to their own format, I guess. There wasn't too much reverse engineering happening there. And it's just generating basically time, right, like a timeline, and it has resources along, as rows, and then the columns here are showing where time is being spent. And so you'll see here, this is one where there's a bunch of little slits over by that softmax, and I'm going to show you guys in a bit when we do the XLA version of this, where all of that gets wrapped into one function, right? Which is huge performance gains. That's the operator fusing. That's what's similar to Spark 2.0 Tungsten. So other obvious ways to monitor your resources, you could do top for CPU on Linux. You could do NVIDIA SMI, which is the thing that we're doing from the notebook. And my buddy's company that is building off of those event files for TensorBoard, he's using NVIDIA SMI and some of the NVIDIA CUDA code to inspect the metrics on the GPU during a training job. Okay, again, I said this is not intro level stuff, but I do want to get to some more key terms here. So for example, TensorFlow model, when people say TensorFlow model, you really have to ask, what are they talking about? And typically their next statement, gives you the context of what they're talking about. But TensorFlow model by itself is a little bit ambiguous. So TensorFlow has the graph, right, which we've talked about quite a bit. TensorFlow also is training variables, all right? And these two are separate. During training and after training, and for whenever you're speaking in terms of training context, the graph and the variables are separate. And that's on purpose. That's so that you could, this graph is static. It's not changing. But these variables do. And so you use the same graph, but can actually start with different variables. Like when you first go to train, you start, right, like not with 0, right, because 0 actually means something here. And you would start with just a random set of variables. So from like day 1, you initialize variables just randomly. There's first class ways to do that within TensorFlow because this is so common. And then the graph stays the same. You train, you train, you train. You then take a checkpoint. That's kind of the term for it, and that's going to write to disk the current values of all of the variables or weights or parameters, whatever you want to call them. It's going to write the values for those variables out to disk. And so that's why when you start with a sample off of TensorFlow website, you're picking up usually like an MNIST checkpoint or the inception, which is the famous image classifier model. You're pulling in a checkpoint file, which was always kind of weird for me to grok. I didn't quite understand why it was called checkpoint. I just kind of accepted it, but it really bothered me until I figured out the terms that are being used. So because these models are meant to, or are capable of being continuously trained, right? Like no matter where it starts from, no matter when you can start from an earlier checkpoint. Maybe this checkpoint was bad for whatever reason. You know, like I said, you were validating in a separate cluster. Sorry, my phone's ringing. Oh, yeah, that was weird. It's a phone number that looks almost exactly like my phone number, just off by a little bit. So if for example, you were validating the model and you realize that it's starting to not generalize, you could then throw away that checkpoint and go back to an earlier checkpoint. Maybe change some things, right? So you can, from checkpoint to checkpoint, actually change hyperparameters, and people do this, right? And in some cases, you could use a checkpoint from somebody else, but completely change the architecture. You would still need the same variables that are checkpointed, but yeah. So these are some things you can potentially play with. So there's graphs, there's the checkpoint variables, and then there's this other concept called a metagraph that's actually broader than just the graph, and it contains something called metadata. And if you've done sort of earlier TensorFlow work, you've seen these .meta files that get written out. And .meta includes some of this data that should travel with the graph. And these are things like any kind of lookup tables, right, that are needed to complete the. For example, with like the image classification, the actual value that is predicted is a numerical value, and something has to convert that into a human readable. Like this is a penguin, this is an airplane, this is, whatever. And so that lookup table has to travel with this graph, because if you swap in a different lookup table, then the results could be completely different, right? And it's just going to be it'll be correct on the numeric side, but the mapping to the human readable is different. So that's why when people say graph, they probably mean the metagraph, which is why if you look on disk and see .meta, you're like, oh, is that really what they're talking about? Or so yeah, just keep that in mind. And yeah, TensorFlow gives you the ability to actually load the this metagraph separate from the variables. And so this is that exact case where you don't care about the variables, because maybe all you want is the graph and you're going to do your own training. You trust that this person has built a graph that works in the image classification space. If for whatever reason you don't want their variables, their weights, then you can do your own training from scratch. Typically, people do what's called transfer learning. They take both the graph and the learned variables, and then they sort of retrain it on a small sample of their own specific domain, right? So if you're running like an Airbnb site or like what's it called? Like Zillow, right? Like places like this, right? Like, was it Trulia? You want to reuse somebody else's variables, and because they've spent all this time training on, and this network has picked up edges and knows what a refrigerator is and knows what a toilet looks like, and so you can then, when people upload images into your like Trulia app or your Zillow real estate app, you can now sort of auto classify, right? Like without a human in the loop, and you can maybe compare to what they think it is, that they're saying this is a bathroom, or you could just get rid of that feature altogether and just rely on your classification. So, but you still want to train it on your own like images, right? So, so that was metagraph and graph. Assets, yeah, are these accompanying assets like lookup tables? Signature def, we're going to talk about here in a bit when we move to TensorFlow serving. TensorFlow serving, so the nodes inside of your graph, right? Within TensorFlow, they're not actually, they're sort of called what you think they're called, like mul and add and w and x. But TensorFlow has the freedom to append, :0 or :1, and this actually happens quite often, especially when you're running inside of a notebook, right, like a Jupyter notebook, because it's very easy to have multiple graphs running inside of a notebook when you don't realize it. If you go to lunch and come back and don't run a particular method, which I'll show you guys here in a bit, which is called reset default graph, you could get into this state where you have multiple nodes that are the same name to you, but TensorFlow has to like distinguish them with a :1 or an underscore, something. So there's this concept of a physical node name inside the graph, and then there's the need now when you go to serve it into like a generic framework. Think of PipelineAI, think of Google Cloud ML. Each time that you train this model and deploy it, those internal node names can change. And what you don't want to have to do is change your TensorFlow serving code to have to know about those new names. And so there's this thing called signature def that was introduced in TensorFlow 1.0, and it's exactly to take care of this problem. So no matter how many times the internal node names change, during training, the final step is to map a well-known, non-changing name, right? If you just called it inputs, for example, and then TensorFlow will map it to the current physical node name. For, in this case, the feed is the X. So, and the fetch is add. In some cases, it'll be X: 1 and add: 4 or something, right? So the problem is that from run to run, from training run to training run, you were putting a burden on the person who's maintaining the TensorFlow serving side of things to have to know and change their code to adapt to some internal detail of how it was trained. So this was becoming an issue specifically for Google's cloud service for handling these deployments. And so they had to introduce this into the open source so that people could use it, so that when they go to upload it to Google, they weren't always scrambling. So like before this happens, TensorFlow serving would just die and say, can't find add: 0, because now it's called add: 1, right? Oh, and then when you go to train, so this is, right, yeah, so again, keeping the graph and the variable separate is because we are potentially going to continue training, or we want to transfer the variables to somebody without using, like transferring the graph for like whatever reason, or just the graph and not the variables. But when it comes time to actually serve the model, to like deploy it to pipeline, to deploy it to Cloud ML, that's when you have to freeze the graph. And freezing, it physically takes the snapshot, the checkpoint of all the variables. Here it's just these two variables, and it burns them into the W and the B in the graph. And so W and B, which were previously in TensorFlow terms a variable, right, which is mutable and has a bunch of extra code around it and safety checks and things like that, has a bunch of bloat, so those become constants, which then all of that bloat strips away, right? And now that's a case where you don't want, or you are not able to like continue training, because you've now like essentially removed the mutable and replaced it with the immutable. You can still keep the mutable version. It's just that when you go to serve, there's a separate step that you do to freeze the model and then upload it to Google or to Pipeline, whatever. Here's a quick note on a session. That's what a session looks like. You could have multiple graphs, like I said. Session also maintains the variables. One note on variables, you want to store those in your CPU. So I'll show you guys how to actually do that later, where you do the with device and give it the CPU, right? Because again, you don't want GPU to be burdened with that. Okay, TensorFlow debugger. This thing's pretty cool. I think I'm actually going to kind of skip over this one. This is one of the exercises, but I think I'm going to skip that because it's just more fun than it is useful right now. Batch normalization. I do want to talk about this. This is super important. This paper came out in 2015. It's a relatively new concept, and so think of the problem. So the problem here is, because we're doing stochastic mini batches that feed into the gradient descent optimizer, however these get shuffled, they're being randomly shuffled, and from batch to batch, if you plot all those values, these distributions can be all over the place, have totally different mean, totally different variance. And so now during training, right, so this network has to not only be doing its main job of trying to learn the weights, but it's also constantly adjusting for this wild change in mean and variance from batch to batch, right? These distributions. So there's this concept called batch normalization, and essentially what it's doing, if you think of it, there's a snippet of code there. Think of it like sort of a moving average. So as data is coming in, there's this sort of final, global mean and variance, and it's per layer, and this mean and variance is this final mean and variance per layer is sort of slowly, right, adjusting to as it sees new batches, and so it's now able, and so at the very end of and so there's two good things here. This is going to speed up training, right, because it's better able to deal with these wild distributions. Yeah, so weights are learned quicker, variables learned quicker. Final model is typically either as accurate or even more accurate, right? So from all of my research, from all the people I talk to, there is no downside to batch normalization. It speeds everything up. It makes everything more accurate or as accurate. And then at the very end, and there's a step for this I'll show when we get to the post-model optimization, the post-training optimizations, you have a final mean and a final variance per layer. What you then want to do is burn that back in to the final model before you go to serve it. That way, so just treat these like these are two more variables that you're learning. These are two more, parameters that are being learned as training is going on. And so when you go to freeze the graph, you also want to freeze in the mean and the variance. And how you do that is one big matrix multiply, right? For each layer, the mean and the variance that are specific to that layer that were learned up till now throughout the training, just do the one matrix multiply right up front and adjust all the weights, and boom, you're done there. If you don't burn them in later, what you're doing is every forward propagation that comes through has to incur at each layer that specific matrix multiply each time. So by doing it once and just adjusting all those weights, now it's just less computations that need to happen on the forward prop, right? But again, this is when you're going to serve and you're freezing the model. If you are continuing to train, you would want to keep the mutable mean and variance just like you would keep the mutable weights. So always use batch normalization is the short of that. I think I'm going to step through this a little quickly too, just based on time. Let me double check here. see, it's so, oh man, do we only have a half hour? Okay, yeah, so let's go through here. Multi-GPU training. So I'm going to talk about this. The way I describe it here generalizes pretty well to the true distributed training. So this is technically single node, right? Like distributed training, you could call it, where the distribution is in hardware, you know, via GPU and CPU interconnects and, you know, buses, things like that. So typically the bus between the CPUs and the GPUs is relatively slow. It still uses PCI Express. I think it's IBM is, with their Power Series, is the first CPU to have the faster, it's called NVLink, which is the NVIDIA, it's a new electrical protocol, or it's a faster electrical protocol. It's not really new anymore. That's typically used between the GPUs. The IBM folks got with the NVIDIA folks to make it so that they can use NVLink between the CPUs and the GPU. So keep an eye out for that if you are using Power Series. I don't know too many people using Power Series, but definitely kind of slick. So what's happening here is, I mentioned the mini batches. The CPU, you know, starts off with, so it's the CPU's job to maintain the state of the variables. The very first thing that happens is those variables get initialized to something random, right? Like definitely not 0. It's the CPU's job to keep those, or to right, like maintain the latest values. Each GPU sees a mini batch and trains its W and B, right? Oh, and so each GPU has the exact same graph, right? Like, so this is most similar to how Spark gets the same code in each worker. Each GPU gets the same mod or the same graph, and its job is to take inputs X, and it's been given the label because it's training, and it's going to calculate the gradients based on the loss. So each GPU sees, so at the end of one full run, each GPU sees 50% of the data, which is why you do multiple runs, right? Yes, multiple epochs, or yes, epochs, which is one pass through all the data. So what happens is every step through, one batch comes in to each GPU. Each GPU is trying to figure out the gradients for W and for B. Each GPU then, at the end of the calculation, has its suggested values, hints as to which way W and B should go, you know, plus 20, minus 2.0, whatever. They pass those hints to the CPU. The CPU, you know, basically doesn't know which one's more important, so it's just going to average, right? So it's going to take the mean of those two hints, of those two gradients, suggestions for each variable. It's going to then apply the averaged update, or it's going to apply the average gradients to the variables. It's going to do the update on the variables, and then repropagate the current variable values to each GPU, and this continues on and on and on. Okay, and so the thinking here is, if you do multiple of these epochs through the data, each GPU will see more and more of the data and not just be stuck at 50% after one pass. So to kind of generalize this a little bit, the left there is a single worker like we were just talking about with multiple GPUs. Right next to it is two different workers. This has now become distributed. So it's using GPU 0 on worker 0 and GPU 0 on worker 1. What's happening here is you write your code the same way, right? Like you don't change anything. All you do is say, I now have two different workers that have a GPU, and TensorFlow will then automatically insert a send and a receive in the appropriate place and can communicate. So just like it would through right, like the NVLink and PCI, or the PCI Express bus on worker 0, it's now doing this across the network. And of course, it's using gRPC and protobuf, right? And so this is actually one of the reasons why distributed TensorFlow took a little bit after the initial TensorFlow dropped a couple Novembers ago, 2015. TensorFlow distributed, which is where the real power of TensorFlow is, didn't come out for a few months until February, March of the following year, was because there was a bit of a holdup on the gRPC being open sourced and some updates that had to happen to get it to 1.0 and some internal systems within Google, because gRPC is so it's so widely used that things had to change. And that's also one of the reasons why when TensorFlow first came out, people were criticizing it so much about performance, because TensorFlow is designed to be horizontally scalable and has been optimized for that, and not necessarily single node, right? Because nothing Google releases is single node. It's just not in their like DNA, right? So when they design something, it's like meant to be scaled, and they very quickly took care of some obvious things, like early on some of the auto differentiation and some of the crux of how these neural networks work was actually implemented in Python. And so very quickly they realized this isn't the way to go. They had to rewrite it in C++, and so that was some pretty big gains. But one of the unfortunate things about TensorFlow, the current state of it is distributed TensorFlow is a nightmare. Not just to maintain the cluster, where you need something like Kubernetes and Mesos, and but TensorFlow, the distributed TensorFlow API has been changing wildly in the last couple of releases. Seems like every talk I go to has someone's talking about the old way of doing it, and this is a person at Google, for example, that hasn't heard about the new way of doing it yet. There's just a lot of confusion. The light at the end of the tunnel is Keras is being the native implementation for TensorFlow is being built with distributed TensorFlow as a first-class citizen. So I'm going to back up one slide. If you recall, the CPU there was sort of our variable holder and was doing the updates. In a distributed sense, and like distributed environments where there's multiple nodes, there has to be some central external body that maintains those variables, similar to how the CPU is acting as that central store. So there's this concept of a parameter server, and this is sort of a legacy term. If this was named today using TensorFlow terms, it'd be the variable server or gradient server, or, something like that, right? So the parameter server is essentially taking all the hints from all the workers. So before it was, I'm going to back up a slide, before it was all the GPUs were providing hints. Now each node that has 4 GPUs, so there's now 12 hints, those get pushed to the parameter server. Now there's and then parameter server acts like CPU. The parameter server for each variable takes all the hints and averages them, and then broadcasts back out that new value for W and B. And of course, it's not just W and B, otherwise you wouldn't need a whole cluster. You could get away with one node, or if you're worried about high availability, if that node goes down, you would want replicas, 2 more replicas living in different zones or regions or clouds or anything. But this parameter server, there's one really cool optimization, and actually Spark does something very similar for some of their inter-node communication. So I was just describing how each GPU has a hint, has a suggestion based on the data that it's seen for each variable. Each node will actually pre-average the 4 hints, those 4 suggestions. And so really the only communication happening is each worker communicates to the parameter server the pre-averaged value from all 4 of its GPUs. So that reduces communication, down O of the number of workers versus O the number of GPUs. That way, if you have 64 GPUs and 1,000 workers, you're not doing 64,000 updates to the parameter server. would just be 1,000. Okay. Real quick, synchronous versus asynchronous. I'm going to back up a slide, actually 2 slides. So I really like this picture here, this figure, so everything I've been describing has been has required synchronous updates. So essentially, the CPU will not broadcast the new variables to the GPUs unless every GPU has shown up with its hint. Right? So that's synchronous. And on a single node, that's probably fine. In fact, that's fine. It's very unlikely that a single GPU is going to die. You probably have bigger problems at that point. And it could be the case potentially where one GPU gets potentially more, no, I mean, just trying to think where one GPU might actually fall behind like another GPU. It's not, per single node, you pretty much always want to do synchronous. The problem here with the distributed is, let's say worker one's network starts to get latent, right? Because this is no longer hardware interconnects, this is Ethernet, right? And so if some of these workers, if the worker either dies, that's actually probably the best case scenario, because you can detect failure pretty quickly and you can, replace it. Training actually can, it will continue on. But if one of these goes latent and then you're requiring them all to send before parameter server can broadcast back out. So that's where problems start to happen. That's where you would potentially want to switch to an asynchronous model. So that would be this here. This chart's not my favorite, and then here's just a quick async versus sync, images per second. So all the big guys use asynchronous, the Facebooks, the Googles, these guys, because they are so distributed. In fact, the benchmarks, the scripts, those will show you how they're doing the asynchronous, right? So they were able to be the best at these benchmarks and have the highest numbers, and it's because they're using async, or that's one of the reasons, is because they're using asynchronous updates. Now, there's a slight chance when you're using the async that you might not converge, right? The problem here is that, let me back up 2 more slides. So for example, if you wait a little bit, if you get GPU 1's hints, but you don't get GPU 2's, you wait a little bit, then you only update. If you don't get GPU 2's, you then continue on in an async manner. You then update only based on GPU 1's hints. And if this goes on long enough, you could potentially, only basically be training with data with feedback from 50% of the data set, and that's not good. Okay, you're potentially working with stale gradients, essentially. Okay, just some other terms: data parallel versus model parallel. Model parallel is, data parallel is what we typically think of. This is how Spark works. The exact same model, just like I was showing with those GPUs, is distributed to every single worker. Just like Spark, the exact same code is pushed to every single worker. Each worker, or in this case, device, GPU or CPU, each device operates on only the data that it's seen, so a partition of the data. Model parallel is kind of the opposite. It's where, there's these goofy terms between graph replication and in-graph replication, which I don't even use because they don't really make sense to me. But this is the case where you literally cannot fit either the graph itself. So before I said for data parallel, you're duplicating, you're placing the graph in the memory of the worker. So if it was these GPUs, right, like GPU 0 on worker 0 and GPU 1 and GPU 0 on worker 1, if the graph itself cannot fit into 12 gigs of RAM because it's such a huge graph, or it requires a lot of pre-processing, so it has multiple graphs, something like that. Or the intermediate, things that, like the sort of temporary variables, I guess you would call them, as training is happening, the temporary variables that are needed by the GPU to even calculate these gradients. Think of huge word embeddings. It's trying to learn these these huge embeddings. If that combination cannot fit into a single GPU, now you have to actually split the model up into multiple GPUs. And this is, classic distributed graph sort of theory. Do you split the model up along the edges, along the nodes? Where do you split the model, right? Like, when does it make sense? I mean, the goal ultimately is to reduce inter-worker, communication because of the network and just the overall probably overhead of all that. So you would really, really have to know your graph really well and know how these things, and you would likely want to split along communication edges of least amount of data being transferred. So you will almost always be doing data parallel if you're even doing parallel at all. If you're doing model parallel, it becomes quite interesting. Okay, so I'm going to skip through some of this. This is just ways to assign kind of roles to your nodes. Parameter servers, like I said, are typically CPUs with a ton of memory, because all they're doing is storing and a little bit of averaging. Workers are stateless and have high compute, so that's a perfect task for a GPU. So when it comes to like Kubernetes, for example, you would label when you spin up your cluster, you would label certain nodes that have GPUs as workers. You would label the high CPU nodes as parameter servers, and then they would perform those roles. I think I'm going to skip through this here. Any distributed system has to have some kind of master. The TensorFlow guys, being politically correct, chose to not use the term master and instead used the term chief, which I think probably they could have done one step better here and not called it chief. But the concepts are all the same. There's one worker that has more responsibility than the other workers. And in this case, in the chief's case, it's responsible for telling the parameter servers to do a checkpoint. So just like I was talking about before, where you take a snapshot, put it to disk, these parameter servers would be instructed by the chief every X number of steps or every time period, every hour, every day, to write all of their current values for all the variables that they're tracking out to HDFS. As I mentioned before, there is most likely a validation cluster waiting to go that'll get spun up every day when those checkpoints are written, and will then validate and pass through the 20% holdout data. And then you would keep an eye on that and potentially stop the training if things go bad. The other big thing the chief does is parameter server health checks. So it's constantly keeping an eye on those parameter servers. The reason why it's keeping an eye on the parameter servers is because they're stateful. And if you lose a parameter server, all of training has to stop until that parameter server comes back up and all of the parameter servers can get restored back to the most recent checkpoint. If you lose a worker, that's what's in the bottom left here. If you lose a worker, that's not too bad. Training can continue. Especially in the case of an asynchronous setup. Not all the workers have to report. This is why at scale, you pretty much always have to use asynchronous because at any given point in time, some node is going to fail, some disk is going to fail. If a region or if like a zone goes down, something like that, right? You can still continue training. If you lose a parameter server, that's actually not that bad. Training does have to stop, and then all the parameter servers have to go back to a recent checkpoint because they need to be in sync. If you lose the chief, this is really bad. And yes, you can have Zookeeper, correct, right? Like Zookeeper or Chubby or whatever can be out there to very quickly replace the chief and re-elect with the new worker. The problem is in that time, a parameter server may have gone down or may have had an issue. And so the absolute safest thing to do, the most conservative thing to do if a chief goes down, is to just roll the entire cluster back to a recent checkpoint and start from scratch. So that's the case where losing a stateless worker is really bad. It's because its responsibilities include rather monitoring stateful nodes and processes. So yeah, definitely want to use Kubernetes, something like that, and some sort of leader election. I've talked about this a couple times. Here's that training cluster with 80% and parameter server cluster. So the training cluster would be the workers. Parameter server cluster is the parameter server is a bunch of CPUs, and upon writing a checkpoint to S3 or HDFS, the validation cluster spins up, and while it has a lot less data than the training cluster, its purpose is to just validate and make sure that the network is not overfitting to a particular set of data. Also, this reduces resource contention. Any sort of things that you might see, like samples that you see or quick demos, people typically do the validation at the same time that they're doing the training, and that's obviously going to use a lot of resources and slow. You're basically going to be slowing down your sort of overall training when you could be doing these things in parallel. There's no reason to do them at the same time if you can write the checkpoint. So real quick, experiment and estimator API. Yeah, the big takeaway from this slide is take a look at the experiment API. This is becoming a first-class citizen, and it's no surprise that Google Cloud, their sort of ML engine service that they use for deploying models, and uses this term experiment. So this is one of those times where sort of product management has influenced the open source project, right? I mean, I saw this all the time with Databricks, right? And it's definitely not evil. It's more a way of seeing how people are using this and what do they need to deploy their models. And okay, let's now create an API that fits them into this particular framework that can then be served. The good thing about Google is that they're actually releasing a lot of what you would think would be secret sauce, experimentation frameworks and the things like the A/B test, frameworks, things like that for TensorFlow serving and version policies and things that they don't have to release that they could hold back to keep a competitive edge, but they're actually producing quite a lot of stuff. Just for one last quick thing on here, there's this estimator API, and this is influenced by Keras, and you're going to start seeing there's a lot of change happening still with the estimator API, but keep an eye on that. That's been in all of the Google trainings that I've seen in the last 8 or 9 months. Yes, I almost feel like the demos and the examples that you typically see haven't caught up to use the estimator API. They're still using kind of raw TensorFlow, but once you start using Keras and once you, at some point, you're going to want to move to the estimator API. Okay, I want to talk a bit about XLA. I think we're running out of time here. All the examples, we can run through them pretty quick, but I do want to cover XLA real quick. So think of XLA as similar to like LLVM, or think of it also kind of like a logical plan and a physical plan, right? So I mentioned this earlier. When you're constructing your graph, you're kind of hinting what you want to do, but maybe Spark takes your logical plan, which might be completely unoptimized, and make it what you really want to do, right? Which is make it fast and combine things in a way that are optimized for the hardware itself and for the engine that's actually running your code. So yeah, XLA, the accelerated linear algebra, has this language or set of operations called HLO, so high-level optimizer. And these, it's a compiler IR. It's independent of source and target, which is typically what these things are. Your graph gets converted into the XLA HLO graph. So that's kind of the logical plan. And then that gets converted into LLVM. And so, yeah, with like LLVM, there's so much support to get from LLVM down into optimized hardware code, right? The instruction sets, that they didn't really want to have to rewrite that because there's already Project LLVM, right? Which is by Apple. And it is fully optimized for x86, for ARM, for NVPTX, right? The NVIDIA instruction set that I mentioned before that you want to pre-warm before doing benchmarks. And yeah, I think I'm gonna spend too much more time there, but yeah. Okay, so here's an example in that upper right is where you'd say with device, XLA, CPU. Here's an example of the instruction sets that's generated. It's essentially unrolling an X squared. And let's see, you can just in time compile at the session level. You can just in time compile within, at different scopes. You can say with this device, or you can even within a device, you could give it with a scope, and just do 1 or 2 lines. At some point, this will be turned on like globally. So essentially at the session level. And you won't even have to think about it. Right now, not all of the operators within TensorFlow, yes, obviously matrix multiply and add and all the common ones, but some of the obscure ones are not supported by XLA or don't have an equivalent. And for like whatever reason, there's code paths you can get into that fail because there's no way to like work around the XLA stuff. So, but in theory, if there is no XLA equivalence, it's just going to fall back to the non-XLA version of these operations, which would just be the normal, matrix multiplier add. But for right now, that fallback mechanism is a little bit wonky. So, which is why this is still the experimental phase. But for the common things, it can do loop unrolling and operator fusing, constant folding. Yes, all the stuff that we're familiar with from SQL optimizations, basically. Here's that chart I wanted to show you, the figures. So there's before and after JIT compiling. So you'll see that's now the scale of these images is a bit off. But just know that all of those small little operations are really slow because they have to move memory from main memory into cache, into the registers, back out the registers, back hopefully into cache, not down to main memory. Whereas if you have one big operation that's been fused together, that data moves in once and as fast as possible, as fast as, like before thread switching happens, or in the case of a GPU, it's just gonna like massively rip through all this data and just do it one time and then spit out the answer. Here's some visualizations on what happens during the operator fusing. So these are the HLO operations, and there's a whole page off that performance site within TensorFlow that shows you what's going on, some constant folding if it's less than a certain value. And this is just a snapshot. This is taking one step into, or like a couple steps in time and showing what's going on. It's actually doing every time that it's able to do a like compilation, it takes a snapshot and you can render it this way. So I think typically, like I've seen as many as 400 steps. It just depends on how quickly it can learn the JIT optimizations. Okay, so at this point, we're not talking about training optimizations. We're only going to talk about predicting optimizations. Here's that AOT. So this is where the model has been built and it's now sitting there and it wants to be served, wants to now serve customers, be pushed behind a REST endpoint or put inside of a Kafka stream. So here, this is this is the XLA AOT compiler. There's this binary that you build when you build from source, right? Like a lot of this stuff has to be built from source. Otherwise, if you just do pip install TensorFlow, like you're not going to get a lot of this stuff, which is why you want to use the Docker images that I provided. Create an executable, right? So this is that thing that you give it a graph, you tell it what are the feeds and the fetches. So in our case, we would give it our linear regression graph. We would tell it the feed is x underscore observed, or x, yeah, sorry, x, and then the fetch is the add operation. So the feed is x, which is the placeholder, fetch is the add operation, and TF compile, this compiler, will go through and literally track, and it's kind of like pulling a thread, all of the physical dependencies from the operating system, from TensorFlow, and the end result is an object file and a header CC library that you can then link into your app. And this is where I was saying, models go from a runtime footprint of 80 megs, with 40 megs from the TensorFlow runtime, down to 600K. The only bad thing here is there's no GPU support, and this is likely because a lot of these small devices don't have GPUs. Again, these, not phones, but more, cameras and really, really tiny devices, right, like typically don't have these GPUs in them just because of power and, cooling and things like that. So this will change, and at some point the AOT, I'm sure, will support NVPTX, but for right now it doesn't. Graph transform tool. This is probably one of the last concepts we'll cover here, and then maybe I'll jump over to the notebooks real quick. So this is a kind of a brute force way. This started off as a bunch of kind of hacked together scripts by a company Google had bought. This person, it's that company Jetpack. The main guy was Pete Warden. Pete Warden now has joined Google, and they picked him up because he's an expert in mobile inference and kind of small device, and it was a perfect fit for TensorFlow, which is trying to move in that direction. And so he brought a lot to the table, one of which is the ability to take an existing neural network and rearrange it, simplify it, do weight quantization where it looks at all the weights and can fit them into 8-bit, things like that. So let's just get right into it. So here's before optimization. This is that tiny linear regression model or graph that at the end of training is completely blown up, and it has all these crazy operators in there that are useful, and you want to keep this if you're going to continue training. The problem is this is not what you want to deploy, right? What you want to deploy is this, or actually this is still even bloated. So this is one run, this is one optimization with the graph transform tool, which is now a framework. And it started off in C++, and now there's more friendly Python ways to do it. So again, if you're a data scientist, you're probably not going to want to be running these even from Python, because it requires a little bit too much knowledge about how the graphs are built and what exactly is fluff and what's real and all that. What you want is some sort of service that you could just upload your model, get back multiple versions, and then you could test those. And so that's exactly what that's the gap pipeline is filling. So here we just explicitly said, starting with a feed and a fetch, go through and strip out any unused nodes. This is obvious. Some of this is making its way into TensorFlow. When you go to freeze the graph, for example, it's going to do as much of this as possible. If you use the AOT thing, of course, because you give it the feed and the fetch, and it's going through and pulling in just the runtimes, of course, it's going to get rid of everything that it can possibly get rid of. So back here, there was still a tiny bit of bloat. There's these identity things that between the feed and the fetch, physically, between those nodes in the graph, there's still these extra things, and these are kind of safety things here. So identity. So we can explicitly say remove those. And these are all examples within the notebooks, by the way. I think it's 8 or 9 or whatever down by the optimizations. So makes the file size a bit smaller, makes the graph smaller. Definitely good from a forward propagation standpoint. But now what's interesting is that you see 3 placeholders, and we know that's not ideal. Only X should be the placeholder. And actually, so I still haven't figured out why. Actually, the big question is, why are they placeholders here versus when we do constant folding, it's able to, yeah, actually, this is one optimization I still haven't figured out, but this is actually more like it. So variable, that's for W and B, and then placeholder is our X. And those are variables because this model still thinks it could potentially be retrained, or this graph still thinks that it could potentially. And so variables, obviously, because they're mutable, have extra things around them and take up extra space in memory because they could potentially change. So here we did fold batch norms. Yeah, we actually aren't even using batch normalization for this small example, so nothing changed there. Here's an important one, and where I'm going with this one, I just Riley backed up a slide, is those variables, when we still need to be converted into constants. That's the final state for this graph. Variables, yeah, we don't want variables, we want constants in there, because that's when we go to freeze and insert. So here's weight quantization. Pete Warden has a really good series of blog posts. Actually, he just had one recently with an update that I still haven't even gotten through yet. There's a lot of content. Pete Warden, W-A-R-D-E-N. He has a really good style of explaining things. He sort of has kind of a common background to, I think, a lot of us in terms of like engineering, and has picked up a lot of this stuff. So the way he explains it is how you would want your friend to explain it to you, not your professor to explain it to you. So I really enjoy his blog posts. This is a case. So if you keep so now that you're done training, you can inspect and look at all the weights, and you can plot all those weights. And you can see if you're keeping those weights in FP32, full precision, you essentially have to store you're storing each value as a full floating point 32. So the size of your model, like the inception model for the image classification, is 90 megs. When you do weight quantization, which is essentially plotting all these weights and then squeezing them into an 8-bit representation. So this is linearly quantizing. This is, super straightforward. You've got your mean, you've got your deviation, you've got, boom, you just squeeze them all in there. Now, you could go to floating point 16, which is a larger range, but yeah, let's just go down to int 8 and see what happens. Yeah, and so this is a case where the model goes from 90 meg down to like 22 meg just by doing this 8-bit quantization, because now each weight, and you're fixing the number of weights, that's going to be the same. It's just how many bits does it take to represent those distinct weights. So after quantizing the weights, the graph actually stays the same, but the file size becomes much smaller, and the compute is much faster. So imagine doing 8-bit math versus 32-bit math, right? And in the case of GPUs, you can fit 4 8-bit into one 32-bit core. Okay? So again, these are just, and yeah, I'll show examples here actually in the notebooks. There's one more kind of complex activation quantization technique, and it's called activation quantization. And again, I would encourage you to go read Pete's blog posts on this stuff. There's a lot of complexity here. There's a lot of kind of different ways to explain it. the gist of it is, I'm going to back up a couple slides. Here we're doing linear quantization because we know all of the weights. They're upfront, they're trained. I can look at the checkpoint file, I can plot them, and I can squeeze them in. There's super easy techniques to do this. And so these are the values. So here's in the upper right, there's your neural network, right? I can't believe I've gone this many slides without showing actual neurons. So there's your X's, coming in. Those are your inputs. Your weights and your bias, one here is the bias. Your weights are trained. Well, actually, one is not the bias. Sorry, yeah, there's no bias here. Actually one with the W0, that is your bias. Okay, so you now have your weights that you've quantized. So you've quantized that W, right, like layer there. Now, there's another set of values that come out of, and so this happens after going through the sigmoid function, right? And that's like the activation function. So in the previous step, we quantized what's on the left, and now what we want to do is quantize the output, the potential output of the forward propagation, right? Because again, the whole point here is to simplify a forward prop. There's nothing to do here with back prop or training. So the problem is the output of the sigmoid function depends on the input, right? Because W and X get combined before the sigmoid function. And so I can't just look at some file on disk, like the checkpoint file, like I did for weight quantization. I have to actually, in this case, this is called like calibrating. Some people call it retraining, but it's actually like more of a calibration step. So what you do to sort of sample or like discover what could potentially be on the right side of that sigmoid function is to run sample data through. And so this is called calibration step. This is not a lot of data. This is on the order of 1,000 images, for example, that you would use against the inception model. There's these, for like KL divergence, these are techniques to, find the saturation points. So it's not quite a linear quantization. This is much more complex quantization, and it does require some training data to go through, okay? And basically what's happening is it's gonna generate many quantized distributions at like different saturation points. This is gonna do it all for you. And then it's going to then suggest, and yeah, you can use KL divergence technique, and you can then get this sort of like newly quantized 8-bit version of potentially the output coming out. So now you've quantized both the left and the right. Now you've got a super tiny model with super simple math, and you're going 8-bit to 8-bit, and life is good. Also, this calibration step doesn't take that much time. This is on the order of minutes on your regular laptop. This is straight out of the documentation. I want to skip over this real quick and show you guys. So if I back up a sec, I'm going to back up. This was the end of our weight quantization. We had the nice model. All we have to do at this point is freeze to get the constants in there. Yeah, everything's ready to go. But because we got greedy and we wanted to see how far we could take this quantization craziness, we now, at the end of quantized nodes, which is actually quantized activations, it's just called quantized nodes in the graph transform tool. Now look at our graph. That doesn't look good. So this is a hint that, oh man, there's got to be another step here. And so this is where you have to calibrate. This is the actual graph that you're going to use when you're doing that like calibration step. Yeah, you notice it's maintaining requantization ranges and doing all those things I was describing before, right? And so, and yeah, min and max. And so after you calibrate, then there's actually one more step you have to do, which is this freeze requantization ranges. That then gets you into the state where you can then like deploy it. Okay. I actually don't have an example of that, so I don't have the screenshot, but okay, real quick, only a couple more slides here. TensorFlow serving, but one key thing here is it's very modular. They designed it to have flexible, customizable, loader strategies, source, where are these models stored? Are they in S3? Are they on a file? Are they, right, like coming from some place super obscure? Are they coming from a content management system? Like, I don't know why it would come from a content management system, but people do crazy things with those things. And yeah, obviously supports all the concepts we know, the graph depth, the variables, the metagraph, assets that come with the metagraph, concept of a version. Every single model that gets deployed has to have a version, and that version, by default, out of the box, TensorFlow serving can only be an integer. This is a slight, it's a slight goofy like limitation. The thinking here is you can always compare an integer for which one's greater, and the default version policy that comes out of the box will always take the highest, the highest version that is underneath the parent directory that TensorFlow serving has been So similar to TensorBoard, where you pointed out a blank, empty parent directory, TensorFlow serving is the same thing. You pointed out the model directory or some parent blank model directory, and you start to insert 0 is one subdirectory that has the model assets, and 1 and 2 and 3. And each time a higher value shows up, TensorFlow serving tries to promote it based on if it's the like default version policy, it's just going, it will always promote the highest one. It'll drain any in-flight like predictions that are happening through the current version, and then it then starts pointing new traffic to the new version. And they've done a lot of tuning around this. There were some early bugs, even as recent as 6 months ago, where if you did deploy a new version, it would totally spike your CPU and put things in an unstable state and slow down all the other like predictions that are happening. Now they've put kind of guards around there to minimize the impact when you do go to promote a version. One thing we do at Pipeline, I would highly recommend you guys do also, have one single model burned into one single runtime. And like by that, I mean, have a Docker image, pull in one model, and that's the only model that that Docker image knows about. So just like you would commit your model itself in, or all the assets that were needed to create that model so that you can reproduce it later, you want to treat a Docker image as just a sort of an executable form of your model, right? That has just a really lightweight, right, like Nginx server that can just take in the traffic and do the request pooling and that kind of thing, and is just passing it back to TensorFlow serving. And then the problem I see a lot of people get into is they want one model server, one TensorFlow serving process to support classification and regression and all these crazy ensembles, things that they're trying. And this makes debugging and I mean, not just log, like going through logs difficult, but also trying to reason through performance problems, right? If you're, mixing heterogeneous workloads in a single runtime, this is always a recipe for disaster. Always think at kind of the most fine-grained. So we don't even let you deploy models, so we only let you deploy one model per like Docker image. There's no way to deploy multiple models inside of a single Docker image. Real quick, yeah, auto scaling is supported kind of natively. We use Kubernetes for this. Again, these are mostly stateless, so you can scale like crazy. You can build your custom loaders to call S3, all that. There's this feature called request batching, which I'll talk about here in a sec, that you can turn that knob on if you have high throughput, a lot of requests coming in. They can get batched up and processed all at once, and I'll explain that here in a sec. You can serve different models or versions of the models in the same process, not recommended, but you can do it. You can actually build custom model types. So by default, it's TensorFlow, which is what you're typically serving. Also, there's a really good hash map implementation. And people ask, why would you do a hash map? And just to remind you guys, places like Netflix, for example, they're constantly their recommendations are like living in a big memcache cluster, right? Yeah, so Facebook uses like memcache extensively, and these are ways you would put, for example, the Netflix customer ID as the key, and let's say the top 100 movies, or like movie IDs would be the value. So having just a generic hash map is very, very powerful, and yeah, not a lot of people pay attention to that feature, but it is there, and yeah, you can customize and add your own. Different version policies, so you can have multiple versions running and be splitting traffic, doing A/B testing. They've been talking about the bandit test. I actually don't know if they've released the bandit testing, but that's the ability to essentially dynamically shift traffic. So if you are doing an A/B test and you're planning on doing it for 2 weeks, by using a bandit, instead of, if B is the clear winner and, after a couple days, B is obviously the winner, you're not screwing all the A people for the next 12 days of your 14-day, 2-week test. You can essentially slowly move traffic over to B, right? And then, yeah, because that's the obvious downside with A/B tests is if there's a clear winner up front, you either have to kill the test, which might not be the best thing to do, or you could slowly shift traffic over and not be losing people because they got stuck into a bad test cell. Request draining, already mentioned. Request batching, I'm going to talk about here in a sec. And obviously, Google loves gRPC and protobuf. Oops, I think I went the wrong way. Okay, prediction service. The original service, there's just a couple more slides here, I promise. The original service was very generic. It just had a predict. And you had to do all of the type conversions yourself. You essentially passed in a tensor and you got back a tensor. Any other type conversions were up to you. They now, and I'm almost positive this comes directly from Google Cloud ML product managers, have a distinct classify. Think of the tooling and things that the more full-featured tools that you can build now that this is a classify versus like regression, right? If you're just trying to deal with like generic predict, makes it like a little bit tougher to render the output screen or things like that, the input screens if you're trying to build a little test like a little test HTML thing where you could test out your classifications. So they shifted. There's this example class that's now a first class citizen. It's essentially a tuple, key value pairs, but it's a little bit better than just dealing with tensor. The list and the output of a classification is a human readable class and your float, which is the numeric output. This is what I was saying. Numeric output, and then something human readable. So the regression, yeah, it's similar as a label there, and in a list of, yeah, so the regression is going to return like a softmax kind of thing. Okay, yes, anyway, let's go to prediction, inputs and outputs. Yes, I already talked about this. That physical node to logical node mapping. I'm going to skip that. This is really cool. So this, I didn't quite grok it until I saw someone using this. And this is a super differentiator with TensorFlow serving than some of the other kind of homegrown serving like layers that you might see written in Python. It's this concept of multi-headed inference. So head in this case is the output. And so multi-heads means multiple output for the same input. So what's happening here is you're not, okay, so you are trying to do a classification. You want to pass in one set of inputs. You want to get the model's classification label, if this is penguin, if this is airplane. That's important, but you also want that final layer, that final softmax layer, right? Show me the actual distribution. It's not good enough to just give me the class and the score, but yeah, right, like show me all of the data that you got. And so essentially treating this network now like a feature engineering, right, like a feature transform that can then be piped into a second model, right, like a subsequent model. So here you start seeing some of these ensembling techniques, right? And so this is a case where you would use this model. It'll give you back an answer, and maybe that's good enough. Maybe you're on a mobile device and that's good enough for now. But in parallel, you want to also take the output, the numeric output of that final layer, and pass it into another model that could give you potentially, if it gives you the same class, then right, like that's awesome. Then that's most likely the class. If there's a difference, then you have to do some sort of mitigation and figure out some way to right. It's just like any other ensembling technique where you get all the answers back and then aggregate them and then produce a final answer. So this, if you didn't have multi-headed inference, what would happen is you would have to make two separate calls. You'd have to, one, get the specific class that was recommended, and then you would have to make another call to get the entire final layer. All right. The gist of this one is, this slide is that TensorFlow serving was recently refactored to be a little cleaner, so you can actually, there's your SO file, and there's your header file right below it. So server_core. This is the case where you want to embed it in your own. So the one clear example is if you're using Kafka and you want to reuse all of the goodies from TensorFlow serving, right, the multi-headed inference and that kind of stuff that you don't want to write your own. You want to embed it right into a C-based Kafka stream connector, right, or a Kafka stream app. Also, if you want to embed TensorFlow serving inside of a mobile device, if you want to wrap it in, circuit breakers and all the nice architecture patterns, if you want to do batch inference, right? So all this request response stuff is all cool and fun, but perhaps you want to reuse this in a offline batch type of scenario, right? Also, by default, this is synchronous. You're passing data in and getting back the response. If you want to convert this into an asynchronous type of pattern, you can certainly do that by building your own wrapper around this. And so finally, we get to the freezing, and I should probably put this slide earlier because it kind of completes that phase. But this is where we converted those two variables into consts, and there's still the placeholder because you still need a place to put the input when you're going to try to predict, and add is still the fetch, so that's where you get the response, but placeholder still needs to be there for X in this case. Okay, this is the last slide here on TensorFlow serving, and then maybe look at some of the notebooks and answer some questions. Request batching. So here, this is like one of my favorite things about TensorFlow serving. At the end of the day, any prediction that comes in to TensorFlow serving is going to require some sort of matrix multiply, right? So if you can, by the power and the properties of linear algebra, if you can combine multiple requests into one big matrix multiply, instead of doing separate small little individual, small is like relative here, right? Think of, it's kind of that same thing I was talking about during training, where you want to pass as much data in as will fit into the GPU. no more, no less. And so TensorFlow serving is maintaining, like this information, knows how much memory that it has, and you can tell it either do 50 milliseconds, 5 milliseconds, 100 microseconds, whatever, or the number of items, the max batch size, right? So this is a case where we know the input is an image. We know that the size of the like average size of these images is something. We can divide that into 12 gigs of RAM that we have in this GPU if we're using GPUs here, and that becomes max batch size. Or we can specify batch timeout. I believe you end up setting both of them, right? Like one of them is a default because one or the other could trigger a batch and then fire it off to the GPU. But the sort of end result is there's one big set of numbers being passed into the GPU once, one big calculation, one big chunk comes back, and because you were able, the offsets of these smaller matrices, you can then carve out the answer and send it back to the specific caller. So these are two independent requests coming in, could be across the world. They just so happen to get routed to the exact same TensorFlow serving process. And so this is one more reason why you want to have homogeneous models, or sort of one model per runtime, because if you start to kind of mix and match different workloads and regressions and classify, the properties of these matrix multiplies could change. At this level, probably it's just going to be matrix multiplies, but there's definitely better reasons to sort of isolate one model per runtime. But yeah, this is something to keep in mind here, that these batches. Oh yeah, and then the other thing too is if you're trying to capacity plan and come up with a max batch size, if you do have one homogeneous model, you then typically know that it's for a particular image size, and then you can better tune and configure. This is kind of a low-level detail here, but by default, if you are using homogeneous workloads, you would just end up using the basic batch scheduler, which is what I was just describing, max batch size, and this is what people typically talk about when they're talking about TensorFlow serving request batching. There's also other forms if you are starting to mix and match. If you do have kind of multi-step inference, like I was describing, multi-headed, if you're doing custom ensembles, then you want to start playing with your own batch scheduling, or start with like one of theirs, and go from there. So, all right, we learned a lot, hopefully, and these are the things that we covered. I do want to look at questions and go through. Okay, real quick. Oh yeah, Bernie, man, yeah, you're having a lot of problems. Okay, Darius asks, how does multi-GPU training affect virtual memory on the first GPU? Most times, first GPU has had greater VRAM utilization than, yeah, that's interesting. I actually haven't noticed that. So I would have to reason through that. And this is, yeah, so obviously this is multi-GPU single node virtual memory. I might have to talk to you about that one after. I have to think through that one, or hear some more about all of the other. Is this, so Darius, is this in, this is TensorFlow specific? The only thing I'm thinking here is because TensorFlow, yeah, this is TensorFlow, because TensorFlow does prefer that single GPU. I mean, a couple obvious questions. Do you know for sure that the other GPUs were being utilized? I assume yes. That's one of those things that is very easy to overlook. You think you're using the other ones, but possibly not. So it just looks like, but it had greater than all the others. So I assume the others were showing up. Yeah, I don't know. That's a really good question. I would also want to know the version of CUDA, and if unified memory was being used, and things like that. Question coming in, is it possible to monitor GPU usage to figure out the best batch size? Absolutely. If TF has full knowledge of the computation graph, why can't it? Right. So there's two questions here. How would you personally monitor GPU usage? Assuming you're the only person on there, the brute force way, obviously, is to pull up the NVIDIA SMI. There's another approach that we use. We actually have a Prometheus connector. So Prometheus is a metrics collector. It's just a time series database, essentially. And you would run your job, and you can, so that job has a unique name, and as that job is running, it's at the same time you're pushing metrics. Actually, Prometheus is a poll method, but you're sending metrics to Prometheus, and it's monitoring the GPU utilization, all that stuff for that time that the actual training is happening. And there's tons of sample code out there for this. There's a library, is it NVML or something like that? The NVIDIA, I don't know, is it monitoring language, or I have no idea what that stands for, but I just copy and paste the code because it's the same code everywhere, where it's basically with the NVIDIA, that tool that we're using, the SMI tool, it's basically how that thing gets to its specific information. The next part of the question is, if TensorFlow has full knowledge of the computation graph, why can't it figure out the best batch size? And so are you talking, is this question in reference to the training or the prediction side of things? Yeah. So training side of things, yes, TensorFlow maintains its heuristics. You're talking about the queuing. Yeah, that's a good question. Actually, on the pipeline side, when you're defining the pipeline, you can specify a batch size. I mean, TensorFlow definitely will know as it's sending to the GPU how much RAM the GPU is capable of. Yeah. Actually, I don't know the details and how much the heuristics would drive. Actually, yeah. Yes, I don't know the answer to that. On the serving side, TensorFlow serving, by the way, when it starts up, gobbles up the entire GPU. So, definitely don't try to serve and train on the same GPU, because you'll definitely hit a ton of out-of-memory things. During training, I have hit on many occasions, actually, especially within notebooks, because they don't seem to close the device and reset devices very well. I have hit out of memories quite a bit, and it'll show up, right away that this thing is full. But yeah, your question's more about the batch size. I think on the serving side, I'm pretty sure that they have optimized with the assumption that they have the full GPU. On the training side, my only thinking is they can't assume that they're the only ones on the GPU. There is a way in TensorFlow to configure and say only get 0.2%, 20% of the GPU for this particular run, and that would have to be taken into consideration. Yeah, these are good questions, guys. We use Google Cloud for other non-ML tasks. We're looking to get started with ML. Using Cloud ML or create our own cluster on the Google Compute. Yeah, the Google Cloud ML API. So they have that concept of experiments and versions, and it's pretty much exactly you know, it's slightly above a bare bones command line, you know, in that it has the same exact concepts as TensorFlow serving. It's just a visual version of them. They claim to do hyperparameter tuning, which, I mean, you can do on your own. You just provide the hyperparameter ranges, and, you know, it's going to do the grid search. Yes, either they'll do it and they'll charge you for it, or you'll do it and they're going to charge you for it on the Google Compute Engine, if you're just going to use that. The one thing the Google Cloud ML stuff is supposed to handle, and I've actually never used it because I've been spending so much time building it, or like something similar. They're supposed to handle the distribution, and that's where you want to use the estimator API and, you know, some of the constructs that are starting to flow into, you know, Keras and things like that. But their claim is that you upload one model, you give it the range of parameters for each hyperparameter, the range of values for each parameter, and they'll do all the distribution and they'll do all the runs for the grid search in parallel. And so, I mean, there's some value in that, and there's actually quite a bit of value in that, because while building that, I've been hitting a lot of weird, you know, strange cases. They'll do all the failover stuff for you, all those, you know, if the worker goes down, if the parameter server goes down, all that kind of stuff. And weight activation, how much those gains carry over if I convert the resulting model to a different framework? I'm quite new in the deal, so yeah. And by converting the resulting model, okay, so I think what you're asking is, this is more a question of, do these other models support? So, Riley, just to be clear, graph transform tool and the weight quantizations are very specific to tensor, or sorry, the concepts are totally generic. The way that we do them in the notebooks and as described here is very, very specific. You know, just the way it's inspecting the weights, and, you know, because it has to know how the weights have been stored. And so the concepts definitely would carry over. You know, yeah, so like I said, these are generic concepts, but there's no way to use the graph transform tool on a Caffe model or a Torch model, even PyTorch, even if, you know, if it's in Python, those frameworks would have to have those constructs. And actually, that's a really good question. I'm going to send that to my buddy who's speaking at the meetup in a couple weeks on July 18th, and ask him to look into that, because he's going to compare PyTorch with TensorFlow and Keras and stuff. When I first read this, I was thinking you meant like batch normalization and dropout and things like that. Those things definitely carry over in concept, but there would, you know, because you're switching over to a different language or a different syntax, right, like nothing really truly carries over except conceptually between these different frameworks. And it's just a matter of, you know, do Caffe and Torch support? I'm positive that they support batch normalization, and I'm positive that they support dropout. We didn't really talk too much about dropout. That's another technique to introduce randomization, right? Like you, during training, if you can cut, you know, 50% of your right, like connections between, you know, each training run, each batch, you just randomly cut 50%. So the network has to learn around that, right? And that's, from an intuition standpoint, that's kind of introducing and preventing noise from being learned, right? And so you're constantly forcing it to focus on the most significant signals, right, by sort of cutting connections. Have to do, we train models with TensorFlow, but we have to do inference using other runtimes. This intermediate transit. Yeah, okay, so the second part of this question is, if you train a model in TensorFlow, want to do inference with Caffe or Torch, I mean, as far as I know, that's not possible. What keeps popping into my head is there's a very interesting runtime by the NVIDIA guys. It's called TensorRT. I'll just type it in here. TensorRT by NVIDIA. Oh, I'm typing it to just panelists, sorry. Tensor. What's interesting about TensorRT is yeah, perfect, nice. Just posted the link in there. And I'm not sure if this is out yet, but they've been working with the Google team. So actually one of my old meetups, I think from April, that's off the Advanced Spark TensorFlow meetup, actually has this talk and talks about quantization. And I've got the technical product manager from like the NVIDIA group speaking about this. This is all recorded, so you can go watch it. What they do is specifically, so TensorRT has the ability to take a Caffe model and convert it into, if you think of it like bytecode, some intermediate bytecode that TensorRT knows. TensorRT, if you think of it, Tensor runtime, this is a highly optimized runtime written by NVIDIA, optimized for their chips. Can take and does all the request batching and the intelligent sizing. They even have like a REST API and stuff too out of the box. So I've been working very closely with these guys, keeping an eye specifically on their TensorFlow. Right now they support Caffe. I believe they support Torch, and they can take those models, they can post-process them, create the like bytecode or whatever you want to call it, that like TensorRT instruction set, and it's supposed to be huge gains. So they've been working recently with Google, and specifically as a step within the graph transform tool. Now I'm not sure if it will end up being part of the graph transform tool, but conceptually that's exactly what it is. It's a post-processing step on your model that can slurp it in and do some of these quantizations. Yes, obviously like they want to take advantage of what the graph transform tool can do, and then take the output of that and convert that into the bytecode, which is why they've been working with the graph transform team. How many people do we have left online here? Oh, actually quite a few. All right, so let me, I'm not going to go through all of the notebooks, but I do want to just highlight, here's an example of building a queue out of HDFS. Can you guys see this? Just make sure. Yeah, you guys can see this. Okay. This is all you have to do. So this is kind of a quick way to do it. There's a convenience method called string input producer that's meant for CSVs and JSON and things like that. You can actually give it to multiple files. Just the way I have this particular single node, PipelineAI, Docker image set up, everything's running locally on localhost. Port 9000 was taken up already by TensorFlow serving, so I had to move to 39,000 on HDFS, but gives you a good view of what's going on here, and it's actually pulling it in. It's not doing much with it; it's just writing it out. But okay, if you guys don't know, if you've used notebooks and you're on a Mac, please run this. This will make all of your matplotlib images super crisp. If you pass it figure format retina, you're basically telling Jupyter that or this is not a Jupyter thing specifically, it's a notebook thing, but telling it to render at much higher resolution. Also, the other trick to these notebooks, always, always, always at the top of a notebook, and actually as you see fit, put in this like reset default graph. As we all, I'm sure, know, defaults are good and very bad at the same time. So this is that case I was saying where if with notebooks, you just kind of naturally jump around anyway, especially if you go to lunch and come back and forget where you were. If you, go from, here back up to here and like rerun it, if you didn't have this reset default graph, it's going to try to, so all kinds of bad things happen, basically. You'll see errors along the lines of variable has already been declared. What are you doing? You're redeclaring it, blah, blah, blah. The other thing people tend to ask about is sessions. Most of the time in examples, if you see like a pure Python example, you'll see, with TF session as ses kind of thing. And this kind of works within notebooks. The problem is you sort of have to now have everything, even in subsequent cells. And if you're rearranging cells like me, I'm always rearranging cells, you can get into trouble pretty quickly. So there's nothing stopping you from just doing ses equals TF session like that. And then everything after that, you just have to specify the session. Here, we're explicitly assigning, so this is the case where we have variables and we explicitly assign to CPU. This is on purpose. If we put it on the GPU, we're just wasting GPU memory. This is one cool thing to point out. This is kind of a slick operator overloaded way in Python to build up your formulas. If you didn't do this, you would have to do some crazy shit like tf.mat mul, w comma x. It's just horrible. So pick that up I had picked that up one time. I was talking to a Google guy and he's like, no man, just do this. So that's a big readability saver. Here again, so this particular notebook, I'm purposely assigning CPU all over the place, because if I don't, because we're on a GPU and because we're using because we've installed the GPU version of TensorFlow will always try to pick the GPU. So here I have to negate that default behavior by explicitly saying CPU, CPU, CPU. So even for the compute bound, I'm forcing it on CPU. And this is just to show that all this can run and how crappy the performance is, and we'll compare this run to the GPU run. Oh no. Oops. Oh, I was changing this last night and hang on. Sorry about that. If you guys had a problem, you can just, from the GPU one, you can just copy this blob up here. Okay, so I want to point out one thing that happened here real quick. So I kind of ran through this quickly, but here's that global initializer thing. This is in lieu of setting all the the initial variables that we're learning to 0, which would be really bad. 0 is significant. So here, and then here I'm just dumping out what those random variables are. So check this out. If I run this again, those variables change. Now it's negative. They change. So every time we run this, it's going to be different variables. And depending on how these, because this is such a small amount of data, because it's such a small network, the accuracy of the final model is very dependent on how these like initial variables were set, right? And so from run to run, you can get wildly different. But now this is interesting. I want to point this out. This is kind of a cool thing. So all I've done here is just randomly generated the start, W, and the B. And now let's assume that we've done no training. And let's see, given let's see how far off we are. So without doing like any training, this is just a convenience method just to tell me the loss for the current, actually probably should be using the validation data here, but yes, anyway, there's no training anyway, so it doesn't matter. Hasn't seen any data yet. So this is really bad. This should be as close to 0 as possible. So we're at 2.4. So obviously we need to train. Why do you use get variable instead of variable? Someone's asking, yeah, Darius, can you post that to the whole group, by the way? Darius is asking, I think there's, is it this thing, get variable versus variable? I can't remember. I remember changing it, and I don't remember why. I believe I would have to look it up. If I change it to variable, I don't want to change it just yet because I want to get through this, but yeah, I mean, hit me up, yeah, offline, unless someone else has the answer to that, but I have to look that up real quick. It'll hit me once I read about it. Okay, so here's the boilerplate for writing out to TensorBoard, essentially. So there's the summary writers. We're introducing ops to actually do the summary writing. Here is the training. Now we've trained, now let's plot it and see how crappy of a fit. yeah, that's not good, is it? So, but the cool thing is we have a graph, so we should be able to go to TensorBoard. So again, if you want to just put in your IP address up here, go to TensorBoard, which is one of the links here. Okay, so we already have, let me zoom in a little bit, looks like okay, so here's our runs. Here's our scalars. So I think there's some crazy values in there. Yeah, so this is using TensorBoard to show both our test and our, so test is actually our validation and train is the training loss. So if we look at just, and you know, they seem like they're close. You can actually zoom in if you go like that, but they're not exactly the same. You know, again, this is because it's there's just not a lot of data, right? Yeah, one thing about TensorBoard, you can zoom in like crazy. If you double tap, it'll go back to normal. That took me like 6 months to figure out. That's logarithmic. If we want to look at our graph, let's go here. We go to graph and boom, there it is. So there's, there's ways in your code to actually simulate this kind of namespacing, scoping so that it does render like this. So for example, we don't necessarily need to know the details of how the gradients is, this is just a kind of a pre-canned operation. Set of code that's been namespaced by gradients, so we can click in and now we can see the actual code in between. And here we can do some stuff. This is also, if we click on device, here it's showing device CPU. So because this is CPU only, so that's kind of cool. Here we can change our runs. We can look at the test run, the training run. Click back on device, everything should be good to go. You can download this if you want. Let's see, histos. I don't think we used any histograms here. Okay, now we're going to actually save this in a format that can be optimized. So here's your checkpoint file. Here's the metadata. Here's your graph right here. And I'm purposely calling this unoptimized just because later we're going to optimize it. PB is protobuf. So there's your graph and there's your variables, right? There's your variables right there. Okay. Let's close it just to be clean. Now, here's where some of the C++ tools, these hidden gems that require a from source build, here's where these come into play. There are Python versions of these starting to emerge. I think TensorFlow 1.2 that I just fully upgraded to recently finally has these as Python wrappers, so you don't have to bust out to Bash and things like that. But for right now, this is showing it's showing 84 nodes. So this is, if you remember, this is the chunk of code I was saying you should totally snag and use in your own projects. This is what generated those graphs, those rather images that I was showing you guys before. So this is unoptimized. This is straight out of training. Here's the random uniform. These things are not valuable at serving time. So, okay, so that's kind of what we're starting with. We can also do the GPU version. This one hopefully worked for you out of the box because I have the imports properly set up. All right, unoptimized. 19 nodes assigned to device CPU, 63 nodes assigned to GPU. Okay, so let's keep on chugging here. Take a look at this graph. This particular graph, I don't believe shows the difference between CPU and GPU. This is why we'll cut over and look. So this should be pretty much the same. In terms of trying to see if there's any difference here. There's one that looks like it might be different. No, tiles there, okay. But we can go to TensorBoard, and this should have recognized it. It's using some magic WebSockets or whatever. We can actually compare a train, run, and between, this looks like this one didn't pick it up. I'm just going to refresh TensorBoard. Okay. We can compare GPU to a CPU training. Where is purple? I don't know what this last one thing is here, but oh wait, comparing train. There we go. So let's zoom in here. And then let's look at the graphs. Oh, and so back on these scalars, what you would do is, instead of necessarily looking at the training, if you look at training and everything looks good, you would want to go look at the test and make sure this thing isn't plateauing or even going up. If this doesn't look like it keeps going down, that means the validation data is not, this model isn't working well for the holdout validation data. So that's where you would want to stop the training. Okay, debug, this is that one. You can follow along there if you wanted to. TensorFlow, I'm going to jump to the GPU version of this one and just show this. So here's distributed TensorFlow. So all a node is to TensorFlow in a distributed sense is a process. And so you can start a process on a different port on the same machine, and that's considered distributed. Now, this is a weird case where each of these is likely going to try to use the GPU, so there's going to be contention. But let's kind of go through this. So here's, I just, copied and pasted some compute-intensive snippet of code there. I'm defining a shape of 2,500 numbers by 2,500. Here's the variable defined that way, by the way, Darius. Okay, and then here's all CPU. So here I'm explicitly saying do everything on a CPU. And we'll see that took 2.16 seconds. Wait a minute. All CPU. Here's GPU and CPU. Okay, so let me show what happened here. CPU and CPU took 2.16. Oh, so right, like what I'm doing here is I'm raising a matrix to a particular power, and then I'm adding those two. And here I'm doing them both on a CPU here. I'm doing one on a GPU, one on a CPU. So the GPU performance helped quite a bit, 1.7 versus 2.16. Now I'm saying do both on a GPU. So look at that, we got 0.24 seconds. That's pretty cool. Actually, I'm gonna rerun this one only because I feel like there's probably some warm up on that first GPU call. So yeah, so we got it down, I think it was 1.7, now it's 1.0. Let's do this again, 2 GPUs, it's really low, 0.23. Now, there's this method here that was introduced a couple releases ago that the Google guys swear by when you're doing distributed TensorFlow. And this is saying, don't explicitly assign anything, just let TensorFlow figure it out. It's most likely going to use round robining, and it will typically always use the GPU if it can. So yes, ideally, like all of our GPUs would be connected. And this replica device setter would actually go and assign work on each different GPU across all of our nodes, each of our specific GPUs. Here, this is a case where it's likely it has to share, but you see it's actually, so us assigning it GPU, and us telling it to just do its own thing, much faster. So as hard as we try to tell it to use the GPU, in this case, likely what's happening is we could, so right, like to me, when I first created this notebook, I thought these two would be the same. Me telling it to use GPU 0 for both A and B, and me telling it to figure it out on its own, to me, this was going to be the same, right? But this actually ends up being faster if you just tell TensorFlow to figure it out. My best guess here, and I really haven't looked into the code too much because again, this is kind of a local, made up example anyway, kind of a toy example, is that we're hitting a case where TensorFlow is recognizing that this is the same local host and it's physically the same GPU, and it's either batching it up into one operation. There's likely some code path that is being optimized for this toy example is what I'm saying. Not like TensorFlow is building code around toy examples or trying to optimize toy examples, but there's just some code path that's being hit where TensorFlow is able to optimize this. My best guess is that it's able to treat these as one single pass into the GPU and kind of doing a request batch style. Okay, here's some of the XLA stuff I want to show you. Oops. Yeah, so this comment here is correct, doing XLA, CPU, and CPU. The point here is that some operations do not have the XLA equivalent, so we still need to use CPU and explicitly assign it. This is something I'm going to keep an eye out over the next couple of releases. I could probably like remove that limitation. So what I'm doing here is the exact same as before, except instead of, and so I'm using CPU here. I believe this was a case where if I use XLA CPU, it would fail because get variable does not have an equivalent, at least at the time I created this, of XLA CPU, so it was crapping out. So I explicitly had to tell it to use, oh, by the way, here's that case where I tried to run it twice, this get variable. This is the goofy error that you see if you're trying to, if you don't call this reset default graph, you'll see this goofy error. So yeah, keep an eye out for that. Don't try to follow what it's doing here. It's not, in this case, it's not the right thing to do. But the variable, yeah, trying to reuse the weights. So I'm just going to go to the top and run it. Here again, we did the random like initialization of the variables. Let's see how crappy we are to start with. Actually, not too bad, but 0.8 is still relatively far from 0. So let's train. And again, we're training with XLA. So we should here in a sec be able to, if you notice, XLA timeline showed up. That's because we had instrumented. Oh yeah, so I didn't show that between CPU and GPU, but we'll compare GPU with XLA GPU here in a sec and see how they differ visually. Okay, so we had a pretty good fit there. We had some good initialization parameters. So let's go back. I actually want to look real quick at, oh, you know what? I didn't show that with the graph on GPU. So if I do device, and here's our legend, there is CPU and there's GPU. So easy stuff is on CPU, hard stuff is on GPU. Let me refresh this. Okay, here's the XLA stuff. I don't know what this loss one business is. Something messed up there. Okay, so the loss is one thing. Let's take a look at the graphs. XLA. So here the legend changed to CPU and XLA CPU. So this gives us a clue as to what operations were able to be like just-in-time compiled and converted into XLA. Now let's go back to, is it here? Looking for one more thing, but I can't seem to find it. They just split out TensorBoard into its own project instead of being part of TensorFlow. So TensorBoard can kind of evolve on its own, and it looks like they changed some stuff here. But okay, and then we could take a look at these timelines. So just real quick to show an example timeline. One thing you have to do here is download this. This is kind of an advanced thing, so don't worry. And yeah, like I said, this is going to be rolled into TensorBoard here in the next couple of releases. But so previously, I've installed the Chrome WTF. I had to download it because I have to upload it this way. Timeline. Where did it go to? Timeline CPU. Okay, so this timeline CPU thing was written during training, and I can kind of look and see where time is being spent. I can actually click on them and look into detail. Start time, wall time, preceding events, following events. So again, this goofiness is going to get rolled into TensorBoard, so you will like literally be able to click on this and it'll show a similar view, where is time being spent and all that. Okay, let me go back to the notebook and finish. Okay, back here. Okay, so again, we're going to write out the unoptimized XLA version. 19 nodes assigned to CPU, 63 assigned to XLA CPU. Here, we're going to generate, so here's that crappy version or the unoptimized version, but one more thing that we're doing here is we're actually generating these things. So this is the JIT compiling. This is kind of a visualization of the JIT compiling. So this was the very first thing it was able to do. And there's a whole page again on these XLA num constant args and all these kind of things. Get tuple elements. These are all documented out there. It's part of the XLA or the HLO, the high level optimizer language. And just kind of progressively, I just was taking snapshots at 10, at 50. So 50, you can kind of probably zoom in here and see what's going on. Looks like it's tackling some of the gradient calculation there. And here it looks like it's essentially, fusing the multiply and the add. Yeah, so that'll give you some good weekend studying to do. Let's do the GPU one real quick. One thing to point out with the GPU configuration, this is called the allowed growth. And if you don't specify this, TensorFlow one notebook will occupy the whole GPU. And so this is where you get into trouble when you're trying to do, like multi-tenant type stuff, where you have multiple people on their own GPU. What happened here? Oh, do I have that same issue with the imports? Yeah, I do. Sorry, I was trying to be slick with the imports instead of just doing them all at the top. Rerunning. Oh, what's wrong with this session? Why does it keep saying that? Oh, this is a weird one. Cold chip level. It's weird. It's like if you do it slow, then it works. I've noticed this. If you set these configuration options, sometimes and you go through too quickly. I thought I fixed that though. Okay. Anyway, let's just get through this. Okay. Oh yeah. Oh yeah. Yes, I know what's happening here. Like when you see those weird issues with the session, it means it's not showing us the real error. It means we're out of memory on the. So the workaround here, and I wasn't even following my own instructions. I skipped right over it. Is to close those guys down, reopen this. And when you close them down, you typically have to hit this like refresh thing up here to get the notebook back again, to get the kernel initialized. So here we are again. We're at the untrained. We're at 1.38. Okay, that one didn't look so good, but Just keep going. So here we got the unoptimized, and we're going to show the graph, and it's going to be ugly. And here we're doing another sample. So one thing about XLA is you will see much, much better results on a GPU than you will if you do XLA on a CPU. In fact, there's some people that would argue they shouldn't have even bothered with the XLA CPU stuff because it's hasn't really proved to be much help. Okay, so here's it looks pretty similar, the similar steps. All right, and let's do, okay, so here's where we're actually using the graph transform tool. Here's Pete Warden, here's his like original blog post on this stuff. One of the optimizations I didn't mention was weight rounding. Weight rounding is pretty interesting. Weight rounding is a technique you would use. So again, you train your model, you look at all the weights, and if you can round them all to a particular rather precision, what you can do is like this is kind of like a weird like way to describe it, but the goal is to make this model, when you compress it, to be smaller. And it's this kind of edge case, or it's not really an edge case, it's just not a very common case where you want to distribute your model out to a small device, or think of ships, right, that you're trying to deploy TensorFlow, these models out to these small devices. You have very slow like networks. You're going through very poor connections. You want the tiniest possible bundle, and so the ability to round your weights. Now, when you go to compress the model, right, you're actually going to do, like gzip on it, compression, like you can actually get it down, 70% of the size. And that's all because you were able to round. And it's, kind of it's a bit related in concept to the quantization, where you're sort of like reducing the amount of bits needed to store the same value. But yeah, it's more of a compression type of technique. Okay, so here, let's just take a real quick look. So we have the unoptimized graph here. We have the checkpoints and all that stuff. So summarize it. It should be the same thing, 84 nodes for that one. Here we're going to do a quick strip unused. So that's the unoptimized. Now we're going to take a look. Optimized, just calling that one strip unused, we now have 7 nodes left. Okay, let's keep going through. So these are these not magic scripts necessarily, but these are what gets built when you build TensorFlow from source and turn all these on. Here we're doing the removing, where we're getting rid of these fluff, these kind of extraneous pesky identities that aren't needed at inference time. Batch norms we're not really using, so it's not going to help. Quantizing, this is going to help. One thing to look at, we're actually going to print out the files here. So quantized. Oh, actually, so removing, when we called the strip unused, I forgot to point this out. Strip unused, so here's the unoptimized, is 12K. When we called strip unused, which was the very first optimization that got rid of all the training crap, except the pesky ones, the identity ones, got us down to 612. When we removed, we got down to 437, got rid of those extra ones. When we quantized, the size of the graph went down, or sorry, stayed the same, because the graph is the same. It's the weights that actually went down. And where would we have seen that? Oh, do you know what? I think on the quantized weights, I think Well, I know you need to tell it where there's a way to pass in the like checkpoint file that it's supposed to adjust. So actually, here it's not doing anything. It's definitely not going to change the graph, but because I didn't specify the location of the checkpoint file, it didn't actually do anything. So sorry about that. I have to fix that one. But the graph ends up being the same size and the same shape. There's nothing different there. Well, actually, that's the one that goes. Oh no, it was the constant folding one that changes it to variables. Anyway, okay. So combining all of them, we go from unoptimized to fully optimized, and there's our fully optimized. So this is nice and ready for constant freezing. I think where. Oh wait, did that? Hang on a sec here. Okay. Sorry, scrolling all over the place here. Okay, so here's the final sizes of everything. Here's the final graph. There we go. All right, and here is the activation quantization. So this is, quantized nodes. And the thing here to show, of course, is that we are not quite done, right? And so this does require 2 additional steps. I'm not doing them here. I need to do them and and then run this freeze requantize, but I haven't done it yet. And then lastly, on the deployment stuff, so just real quick, I want to point out, we probably should wrap up here because I think we're we're an hour and a half over. Oops. Just want to show you guys this. So this is the actual freezing step, right? So here we're taking the fully optimized graph and we're freezing it. So this is why we have to give it the checkpoint file that contains the weights. So let's freeze it and take a look at it. Oops. If you're in this situation, it's likely you have to restart the kernel thing here. This is just kind of tacit notebook knowledge that we pick up. And there's the constants, exactly what we're looking for. Do I print it out? Yeah, right, frozen. So 247, so see how we went fully optimized is 437. When we went to freeze it, it's 247. And that's good because, or that happened because we converted variables into constants. So a bunch of fluff that's required for this to be mutable goes away. And then this is kind of cool. There's this benchmark utility too that got built when we built from source, and it lets you analyze at every operation level. So, and here you can even see GPU mem copy, device to host. So average, 0.03. You can see what percentage it's taking up. You can see what's actually causing it. Top by computation time, top by memory use. So this is a nice little handy utility. This used to print out a bunch of crap and it was difficult to read, but now it's actually somewhat readable. And here we're gonna reset the graph. Now what we're gonna do is actually prepare this for deployment. So we've frozen the graph. Now we need to, here's where we're doing that signature depth mapping. So we're saying everything is always going to be called inputs. Internally, there is this utility method predict signature to create a predict signature def. I'm still using predict. I haven't switched over to classify or the regress. I just deal with the tensors. Here's this mapping. So it's the human, it's the well-known logical and the physical. And this utility generates this for us. And I think we can print out predict signature. Let's see what it prints. Yeah, so here's the signature here. We delete that, delete that. This is the signature, inputs, outputs, and it's of type predict. That would be classify or regress. And now we take the fully optimized model and we convert it into, so this is the new way now to store models when you're getting ready to serve them. And physically on disk, I think I printed out here, is this is the directory, and I'm purposely using version as a timestamp because I know time is always increasing. So I'm using timestamp as a version number as like integer to pass in, and these are the variables. I'm going to close this, and now I was just changing this earlier today, so hopefully I didn't screw anything up. But if we bounce out to a terminal, okay, so it recognized that version right there, so that's cool. So that's TensorFlow serving. I'm purposely turning off batching just because that's one of the knobs that we'll turn here in a sec. Oh, I actually have to start. So there's something else I need to start. This proxy here. So this is just a quick tornado proxy. This is what a lot of people do, where we have a C wrapper now that will do the HTTP JSON to gRPC protobuf conversion. But for right now, for this demo, we've got just Tornado running, similar to Flask. Supports async. It's kind of nice. And now I should be able to go to this thing and do predict. I didn't screw anything up here. Okay, first time through it. Takes a little warming up. So this is using a GPU. Let's double check that. Found device here, found the Tesla K80, so of course it's going to use it. You'll notice there's these warnings here in TensorFlow Serving. The version that I built for this particular workshop, I actually have these disabled, these optimizations. These are Intel optimizations, the AVX and SSE4142 FMA. I was having problems. I was in Europe recently doing this workshop, and I was being allocated onto the Google instances that had Intel chips that didn't support these optimizations, and it completely shut down the workshop. So, and at one point I was building both versions, and I realized for workshop purposes, I could just get away with kind of doing the lowest common denominator here, but you definitely want to turn on these Intel optimizations, and it's in my Docker file, and it's just one line you have to uncomment out to turn them on. The problem is you need at least, I believe it's the Haswell or Skylake, or it's like one of the newer chips. Google now lets you actually select the minimum that you need from Intel. That was not available when I was in London doing this workshop. and like literally, I created a help ticket with Google, and like literally a week later, yeah, my buddy emailed me and said, yeah, we actually took care of that. It's now like a drop down on the console. So I could actually turn these back on, but for safety, I just, yeah. So Darius is asking, is the Docker file with the optimized TensorFlow? Yes, it is. It's probably worth just sending you guys a link in the little thing here. So I always go to PipelineAI myself because I can't remember where I put these things. I go to GPUs, gpu.ml. So actually, this is the workshop. Yeah, so let's start here. I'll just start here and show you. Docker file, CPU, GPU. This is if you want to get it working on the CPU. Okay, so this Docker image that we're using, this is the exact Docker file that builds this workshop. References this. And if you kind of follow me a sec here, you will see the backup one. Oh, sorry. There is this package.ml. If you guys don't like remember this, just shoot me an email and I'll definitely share it. So my naming convention here is the first one is TensorFlow, the first 7 of the commit hash, and then TensorFlow serving. And I do this instead of pinning it to a specific version because I'm always trying to pick up features before they're either fully released or one particular commit has busted the build, so I have to, and trying to find a good combination of TensorFlow serving with TensorFlow gets tricky. TensorFlow serving releases about twice a year or something, and TensorFlow releases every couple months. So I'm constantly in this situation where I need a feature from TensorFlow serving, and the only version or the best version that works with TensorFlow is this or whatever. So that's the naming convention. But just to kind of show you, and full CPU versus non-full. Full is where I'm building all of these tools. So I'm building benchmark and I'm building summarized graph and I'm building a lot of these nuggets. If you don't need that, and it builds a lot quicker if you don't, you would just go to the non-full version. But let's take full GPU, which is what we're using here because we have all these turned on. Let me just search for AVX. And this is the one line that you have to comment out. And if you run that, you will get all these turned on. I believe it's for both TensorFlow serving actually, and for so if I just search AVX again, should show me the next line. Yep. So this is the TensorFlow build TensorFlow. This is all in the same image Docker file. I first build TensorFlow serving, then I build TensorFlow. And this is all up to date with the latest Bazel, which is a pain in the ass. And what I do is, and I've got the latest CUDA here, 361. Yeah, so what I do is I do a git clone and then I just reset to a hard version and keep my fingers crossed and make any changes I have to. Also, I'm up to cuDNN 6. This is the latest and greatest, CUDA 8. Keep in mind, if you're running on an older, if you choose to save money and run on the G2, you have to change the compute capability here to 3.5. I can actually cross compile and do both 3.7 and 3.5. So CUDA has this concept of a CC, like like compute capability, and this directly maps to what hardware you're using. So of course because I can never remember, so I just put them in here. And if you do cross compile, you do 3.7, 3.5. I was having some weird issues with the GPU build a couple months ago, and I just dropped the cross compile just to make sure that that wasn't the issue. One thing I would recommend, if you guys do want to go off and build your own and maintain your own separate build of TensorFlow serving or TensorFlow itself, check out ci.tensorflow.org. I'm on here all the time. It seems kind of ridiculous, but you go find your particular configuration. Where is it? TensorFlow. So for example, if you're looking for Linux and then XLA, you would click here and just literally go in and look at a recent successful build, look at the console output, and scan this thing for any goofy flags that you weren't aware of. And this is really the only way to keep up. The documentation on these sort of more advanced, obscure features is totally lacking. So, what is it? Oh, it's the full log that you want to. Yeah, make sure you click full log. And then all the answers are revealed here. There's this goofy Py3 script that I needed to look at and adapt my build to. And this is where I saw where they were using cuDNN 6 and not 5. And so I thought maybe that was the issue. So I upgraded. There's these weird things you have to do in the build to temporarily copy things into the right place and CUDA. Yeah, so, or just stick with my stuff. Yeah, Rahul, thanks, man. I think we're pretty much done. We got this end-to-end to predict, right? I think I have a load test. One of the fun things to do. So you can run load test, and just high, medium, low is kind of the relative settings. Yeah, obviously we're going to do high. Who would ever do low or medium? That's crazy. You can also simultaneously, so I have a window up here, I have another thing here showing NVIDIA SMI. So I'm a fan of JMeter. It's kind of ghetto and it's kind of old school, but I know its quirks. So, oh, yeah, Darius, you have predict. Did you? Okay, Darius is having an issue where his predict is giving a fallback. This typically means that TensorFlow serving didn't start properly, or maybe you forgot that step, or TensorFlow serving started up and you haven't built the model. So for example, this is one of those things that you have to have done a step before. If you can copy and paste in the error maybe that you see when you start up. The other thing too is possibly go and kill all of your notebooks. Because as you can see here, I'm highlighting it. TensorFlow serving likes to take up as much memory as it can. So here we see, about 300 requests per second. Average latency about 200, 300 milliseconds. Oh, which flag, Darius? Is this something I should change? Okay. Okay. Got it. Yeah. Funny enough, in the latest PipelineAI stuff, we actually moved away from the underscores for model name when we started to use S3 as the model, as on some customers are storing their model hierarchy inside of S3, and S3 doesn't like underscores so for the bucket names. So hyphens have been in favor. Okay, so I'm killing that load test. One thing I wanted to do, there's a way, so the batching, turning on batching has become more complex. It's not just this anymore, the enable batching. And I think it's, actually I do this in, yeah, so the gist here for the next notebook is just deploy the unoptimized version, and it should be a little bit slower. It's actually not that much slower because it's such a small model, so I'm not going to spend too much time there. But I believe these settings don't actually work anymore. I think there's a different way to do it, but let's give it a try. Let me kill TensorFlow serving. All right, so does it look like any batching? There's a new way now in TensorFlow 1.2 to configure batching, like request batching. But let us run this anyway and see if there's any difference. So latency went down quite a bit, but I'm waiting to see if that is just things. Yeah, see, I don't think the batching has actually been turned on here. One of the metrics that we're trying to get exposed from TensorFlow serving out to Prometheus is the batch size, so we can truly, monitor that that's turned on. Yeah, the question on the chat is, what exactly is the load test doing? This is one of those magic scripts. So Darius, if you want, you could do which load test like that, and then copy that and cat it. And that'll tell you exactly what it's doing. It's just, yeah, so it's still really not that clear, but it's running JMeter and JMeter inside of this JMX if you actually wanted to crack that open. Just for your own purposes here. Oh, something happened. You can look at the tests. Predict high. It's pretty readable, but yes, I know that there's better, load test frameworks out there. I just happen to have these things handy. So it's doing 100 concurrent threads. It's a 30-second ramp up time, which is why we see low latencies at first, and that, for the first 30 seconds, it's slowly ramping up. And then it's just continually pounding it. So yeah, the new way to, if you're interested, the new way to get, oh, by the way, yeah, so deploy.ai, this is going to be the first pipeline product, the official pipeline product. This is where all the new development's happening for all this stuff. So the new way to get, where would it be? The new way to turn on the request batching. It's in this run method, actually. is like this. I just want to see if this actually does make a difference. And then I need this config. Basically, I think what was happening was they started adding so many new parameters that they finally decided just to move to this like dinky config mechanism instead of the just continuing to add on. The model name, what is this model name? Is here port 9000. And I think we should wrap it up here. If anyone has any questions, please post them or shoot me an email. Or if you're using Pipeline, help@PipelineIO notifies all of our phones and yeah, no matter where we're at. So that's how my friends get a hold of me to hang out with me anymore. It's through the ticket system because I don't really check email that stuff. There's just too many emails. Okay, let's config tf serving batching config. All right, Darius, thanks, man. Hope you have a good weekend. Yeah, I didn't take you guys away too long. Let's do one last thing here. Batching config. TF serving. Yeah, the question from Rahul. Yeah, so thanks everyone who's all like checking out. Do we get the GPU instance in the cloud with Pipeline Community? This is something I'm working on. Actually, I was working on it this week. I was trying to get a good build. What was the problem? The problem is Kubernetes and GPUs. So Community Edition, we're relying on Kubernetes. So the short answer is this is coming for sure. And right now, though, yeah, you would have to follow the steps off of either PipelineIO, which end up pointing you to the wiki, the FluxCapacitor wiki. So GPU instances on Community Edition will be coming. We're actually going to package that up with a couple other cool things too, with some cool dashboards and stuff. So by end of summer for sure. Yeah, good question. That's been coming in quite a bit. Everyone loves GPUs. I can see like people log into the Community Edition and they start they bust right out to a terminal and they start running the commands to see if there's a GPU on there. You know, they're running the NVIDIA SMI and all that. So that's what you guys want. That's what we're going to give you. Just don't do any Bitcoin mining on there, please. Okay, let me try to run this. So it'd be tf serving batching config dot txt. Okay. Oops. Oh, batching parameters file. The question was asked about recording. Yes, is this still, let me just double check that it's still recording. Yes, yeah, so I will certainly post it. I've actually posted a similar one from a month or two ago. I think I was in London doing a similar talk. So if you go to, PipelineAI, go to the bottom right, there's those little indicators that'll have YouTube. If you can find an older version, but it's basically the same stuff. I've certainly added things since then, but you have access to all the notebooks as well too. So everything gets posted. Yep. Okay. And I'm not really going to introduce anything more. I was just going to try to get this to work if anyone wants to see the batching parameters file. Isn't that what I used here? Let me do. Okay. Think. Aha. Just. So start it up. It should have those batch parameters. Let's try to run, see if there's any useful improvement. So load tests. Just the 30-second ramp up. So what do I have? What's interesting is that the latencies will likely go up, but that's expected, right? Because depending on how I have it configured in the config file, which I don't have in front of me yet. Um, 10 milliseconds, number of batch threads, max batch size 256. It's likely hitting the batch size of 256 because it's before it hits the 10, because this is not a lot of data. Let me just make this higher. because we're purposely telling it to wait longer, yeah, I don't think that's a very good test. Okay, yeah, this will be the last run here. Like it was doing a lot more per second before. Anyway, yeah, so those are some ways to tune it here. Okay, max batch size. Was I doing it? I think I was doing it that way. Micro, so 10 millis. Okay. All right, guys. Thanks so much. I think it's 5 o'clock out there. We were supposed to end at what time? 3? So awesome. Yeah, shoot me an email if you guys have feedback. Yeah, obviously not enough time. Yeah, that one I know, but I figured I'll give you more than less. So hope to see you guys around.